Good morning and a very warm welcome to the third day of this 5-day e-workshop on energetic beam technology from material engineering to diagnostics. Now, I would request my colleague, Dr. Jagjeevan Mittal, to take over the proceedings of the e-workshop.
Thanks, Dr. Richa Krishna. I welcome all the participants. Now I will ask Pooja to introduce the Yukiko Yamada. Pooja, okay.
Good morning, everyone. I, Pooja Bhattacharya, along with my faculty coordinator, Dr. Jagjeevan Mittal, welcome all the eminent speakers and participants for day 3 of e-workshop Energetic Beam Technology from Materials Engineering to Diagnostics. The first talk of the technical session will be delivered by Dr. Yukiko Yamada Takamura. Dr. Yukiko Yamada Takamura has received doctoral degree from University of Tokyo and did her postdoc in association with Max Planck Institute for Plasma Physics in Garching. Later, she joined Institute for Materials Research, Tohoku University, Sendai, as a research associate. Presently, she is working as a professor at the School of Material Science, Japan, Advanced Institute of Science and Technology. She is an eminent member of the Japan Institute of Metals, the Japan Society of Applied Physics, and the American Physical Society. She is also active as an associate editor of an open access journal, Science and Technology of Advanced Materials, published by NIMS in collaboration with EMPA. Today, she is delivering a talk towards experimental realization of a new 2D flat band material. On this note, please join me in welcoming Dr. Yukiko Yamada Takamura. The virtual platform is all yours, ma'am, and you have 45 minutes to deliver your talk, followed by question and answer session of 10 minutes. I humbly request you to please conclude the talk in this timeline. Over to you, ma'am.
Thank you very much for your kind invitation. So I will share my slides. So thank you very much for your kind invitation to this e-workshop. I have given a talk last May, 1 year ago, and given a chance to talk in your seminar. And I'm very happy to give you some updates of our research in this workshop. So today I made a title like Towards Experimental Realization of a New 2D Flat Band Material. And this is the main research project I'm working on with the support from JSPS Kakenhi in my school. And our school is called Japan Advanced Institute of Science and Technology, but it's a graduate, what we call graduate school university. And we have School of Material Science, Information Science, and Knowledge Science, and have master's students and PhD students, about 1,200 students and about 150 faculties. Very small compared to your grand university. And so before I go to this flat band material, I would like to introduce some original 2D materials I was working on, and some stories I've given you in the last seminar. So the king of 2D material, I think you all agree that it's graphene. So for the research of graphene in 2010, Nobel Prize for Physics was given. And then, so what is fascinating about the material graphene is this, in its freestanding form, it gives a direct cone in their electronic structure. So this is sort of a toy model, two-dimensional honeycomb lattice. And then like a tight binding calculation in its electronic structure close to the Fermi level. You see this dispersion, which is like a photon dispersion. And actually in the material, when you prepare properly, you see these kind of feature, which was a big surprise back in 2004. And now we're interested in material which have similar properties and structure, but made of other material like silicon or germanium, which is a bit heavier than carbon. And then in theory, it is predicted that silicon and germanium can also exist as this kind of a buckled honeycomb structure, and the electronic structure would be similar, like having this kind of dark cone. And so this goes back to the talk I gave a year ago, and this is the system when Professor Bera was a postdoc in my group. We built apparatus which we can grow a film of zirconium diboride, which is metallic ceramic, on silicon wafer. And we were interested in this material. So zirconium diboride is a metallic ceramics, and it consists of HCP metal zirconium layer and boron honeycomb layer. And then this material was very lattice matching to gallium nitride, which we use for white LEDs and blue LEDs nowadays. So we were growing this film in a single crystalline way on silicon 1-1 wafer, and we saw an interesting reconstruction in reed. Then in STM, we revealed this kind of very interesting reconstruction, which was never seen on a single crystalline zirconium diboride. And then we took a close look with our colleagues, which were experts in synchrotron radiation facility measurements. And here I show some core level photoelectron spectroscopy done in Photon Factory, which is a small, relatively small synchrotron in Tsukuba in Japan. There's also an Indian beamline in this Photon Factory, beamline 18, but this was measured in beamline 13B. And so here, the panel B is the measurement data for our zirconium diboride surface. And apparently we see a very clear silicon 2p core level peak with a spin split. And also we see three kind of different chemical environment for this kind of silicon. And this was quite amazing because if we do similar kind of XPS in our institute using aluminum K alpha or magnesium K alpha, this thing were just observed in a broad peak. If we go to synchrotron, we can clearly see this kind of very fine feature. And if you compare it with other people's published data, so this spectra on the right side is for silicon 1-1-1 surface, you see that this silicon is not like that we have a substrate exposed. We really have this silicon on our film. And then our colleague tried to calculate. So we had this unit cell, which we derived from our reconstruction. And we also put silicon atoms to meet these almost 1/2/3 ratio. And then we find that we have a honeycomb silicon on this zirconium diboride. And then our first principles calculation colleagues calculated there's a two stable structure, one ground, one metastable. And then we found out that there's one is this planar-like, what we call planar-like structure, which the 6 out of 6 silicon atoms, 5 is planar and 1 sticking out. And another one is buckled like, which we call, so it's buckling, but not like freestanding silicene, which is the silicon virgin graphene, but buckling in a special way so that it's 2x2 reconstructed in terms of zirconium diboride and actually root 3 by root 3 in this silicon honeycomb structure. And then, so here I show this method and result papers. Our colleague managed to develop a method to calculate the binding energy for these two structures. And then the result he got for this ground state is on the panel D, and for this metastable state is for panel C. And you can clearly see that the experimental result fits very well with this planar-like structure. So it seems so this is not a direct derivation of structure using diffraction method, but from this core levels photoelectron spectroscopy in the synchrotron radiation facility, and also very high level first principles calculation give us that the information that the structure should be this planar like ones on silicon layer on zirconium diboride. So, and then I will show you another measurement done also in synchrotron radiation facility at the same beamline. So this is the left panel is angle resolved photoelectron spectroscopy, which gives you an idea of the band structure of this material. And then, so the same colleague did the calculation for ground state and metastable structure, and then unfold it to 1 by 1 unit cell so that the comparison will be easy. And you can also clearly see that the band structure calculated for planar-like structure, which we find very consistent in the core level spectroscopy calculation, fits very well, while the other structure do not. And so our conclusion was that freestanding silicene, which exists in the, well, only in the computer probably, had the Dirac cone, but when we place it on our metallic substrate, the structure changes. Dirac cone gets destroyed. So this is the key point of silicene honeycomb lattice, and you see that Dirac cone is destroyed, although it have a PZ character, and now it's gapped. And then also the structure I told you before, but it's very different from the freestanding one. So experimental realization of this kind of freestanding honeycomb lattice made of silicon and germanium is quite difficult compared to graphene, which is perfectly stable. But since we have this sample, so this zirconium diboride film grown on silicon 111 was very useful, because when we bring it to synchrotron radiation facility or other kind of experimental setup under UHV, we can reproduce this silicene material very easily. So we use, well, the results were published in PRL in 2012, but this is the material we use for research for quite a long time. And in last 2 or 3 years, we published a number of paper with a number of colleagues, and most of the paper includes measurements at different synchrotron radiation facility. For example, I think this kind of heterostructure I talked in last year in your seminar, but the measurement was done in diamond light source, which is in UK. The other, like UV SOR 3 or Photon Factory, Spring 8 is in Japan. And probably you have never heard of this SPF, slow positron facility, is what I will put emphasis in this talk, which worked very well to reveal the structure of unknown 2D materials. But I'll come to that point later. And so first of all, I would give, so before going to flat band material, I will give some talk on the most recent published paper from our group, which is published in Physical Review Materials as a letter this January, which we did the measurement of for core level and also ARPAS in UV SOR, which is also small synchrotron facility in Aichi Prefecture in Japan. So 2D silicon germanium alloy with honeycomb lattice was calculated to be, so this is all freestanding, a topological insulator like silicene and germanium. But an interesting thing is that its spin orbit gap, band gap, steadily decreases upon increasing silicon, which is different from bulk 3D silicon germanium alloy. And how can we make this kind of material experimentally? So then, so this is the same slide I showed you before. So we use this silicene made on zirconium diboride film on silicon as a base. And then one of my students deposited germanium on the surface and then anneal it at 800 degrees Celsius. And actually it melts. And then it recrystallizes at room temperature, well, below 650 degrees Celsius. Then the STM image looked like this. Before, you also saw stripe pattern, but you did not see these kind of bright features. So, and when you increase the amount of germanium deposited, this bright feature increases. And the difference in protrusion, it doesn't seem like an add atom. The difference in, well, one measured in one kind of bias voltage was around 25 picometer or so. So it seems that bright protrusion is germanium atom, which are included in this honeycomb lattice. But this temperature had problem because we also have segregation of silicon from the substrate to the surface. So my colleague found a better condition. So if you deposit germanium at 350, which the segregation of the substrate is suppressed, you can increase the number of germanium incorporated into the silicon germanium lattice. And it seems that when germanium is there, silicon is kicked out and germanium wants to, well, silicon lattice wants to welcome germanium in their lattice. And then by precisely controlling the amount of germanium on the surface, my colleague succeeded in having, so this is the beginning material, 100% silicon. And by increasing the amount of germanium, he increased up to silicon 5 germanium. So 5:1 ratio. And then, so this is the core level spectroscopy done at UV SOR for germanium 3D. And you can see that the amount of germanium increases. And then, so the interesting thing is about, so that the band structure changes gradually upon the admittance of germanium into the silicon lattice. So first of all, this planar-like silicene structure on zirconium diboride, which is made of 100% silicon, the top of valence band is around this energy. And then when we increase the amount of germanium, it seems that germanium atoms randomly replace these sticking out silicon. And then the top of valence band gets closer and closer to the Fermi level. And then by reaching silicon 5 germanium, which means that the on top, these silicon atoms are replaced by germanium, the top valence band reaches at this level. And this fits very well with the first principles calculation done using the same model. So we can we can possibly control the band gap of this two-dimensional silicon germanium alloy and this band gap difference. So this is not spin orbit induced gap like the one calculated for the freestanding two-dimensional silicon germanium alloy, but this is silicene on zirconium diboride, so it's different. But it seems that the gap becomes smaller for the material including germanium, like three-dimensional silicon and germanium. So then, so this is another experiment done by my student, but when he deposited germanium and didn't raise the temperature as high as 800 degrees Celsius, he saw that the silicene part and germanium, well, we were first thinking it was germanium, but this part splits up And when you look closer to non-silicene part, you see root 3 by root 3 reconstruction. And this is actually the one thing interesting is that germanium, I don't know it's because of surface energy or affinity to zirconium diboride surface, but would like to replace silicene. So silicon is kicked out from the surface and now it gets covered with germanium. And so this layer is very, very stable. And then, but we could not decide the structure at all. So the two-dimensional Brouwer lattice for this kind of symmetry is there's only one type, hexagonal lattice, but we built a lot of models, did calculations, compared the band structures, but it was really, really difficult to come up with a single possibility. So now I go to the next. So the flat band comes later, but so we first of all looked into the structure of this germanium lattice and then find out that this was actually a flat band material. So what we did was that instead of having silicon as a substrate with having germanium, we could form some two-dimensional germanium layer on zirconium diboride. So our first intention was to make a direct cone, a material having direct cone, like germanium. But what we got is the same, this root 3 by root 3 structure, which doesn't seem to be a honeycomb. So what is it? Was our long-standing mystery. So growing single crystalline zirconium diboride film on germanium 111 wafer was quite easy. One of my sub-theme students has done it. An interesting thing is that we can also bring it to synchrotron radiation facility, heat it in under UHV, and get all the oxide-related layers gone. And then you see, so these kind of black spectrum is oxygen related peaks. This experiment was again done in Photon Factory at B-13, but after annealing for a while, this oxygen and also oxide related peaks are gone. And you have this root 3 by root 3 reconstruction again. And then when we do core level to see if germanium is on the surface, there is, like we see a peak, like the ones when we deposited at germanium. And so it seems that germanium from the substrate also segregate to the surface and form this kind of two-dimensional structure. And what could be the structure of this layer? And for this, we seek out for collaboration and then collaborated with a group who are doing total reflection high energy positron diffraction. So positron is an anti-particle of electron. And in Japan, there's a beamline where you can do trap, what we call trap, which in electron, it's like read. And so this kind of project was led by Ichimiya sensei and Hyodo sensei in Japan. And first of all, I will explain why positron diffraction works for 2D materials. So experimental setup is just like read, and it's just that you have a positron beam instead of electron beam, and you have a screen. And then here illustrated are the potential energies experienced by electron and positron inside and outside the material. So where electron sort of easily get into material, positron, because it have a positive charge, it experiences difficulty in getting inside the material, which the core have the positive charge. And here's the glancing angle. So the detail is in this paper written by Fukaya sensei, who is our collaborator. And this is a review. And you can see that here's a glancing angle, theta, which is this angle, incident angle, and then the probing depth this is actually for silicon crystal and is calculated. And up to about 2 degrees, the positron experiences total reflection, whereas in case of electron, it goes quite deep inside the material. So this is the difference of depth proved by the method REPT, or in this case, because it's totally refracted, we call it TREPT, and also RED. So in this total reflection range, positron just go about an angstrom or two at the very surface, while this electron probes 1 nanometer or so. So it have an extremely high surface sensitivity, and Fukaya sensei is collaborating with a lot of 2D materials group to decisively measure the structure. And it's really, really powerful. And it proved to be very powerful also in our case. So, and this could be done in SPF, which is a slow positron facility in KEK in Tsukuba. And it's almost, I think, downstairs of a photon factory. And what they use is this Linac-based high-intensity positron beam. So using a very dedicated Linac, which accelerates electrons to 50 mega electron volt, this electron beam is shining to a tantalum plate. And then the Bremsstrahlung radiation forms electron and positron pairs. And then this positron is then led to tungsten foils, which have negative work function for positrons. And then it's thermalized. And then this positron is accelerated to about 10 keV and used for this kind of measurement. And because of this Linac-based positron beam, it has a high intensity. It's very bright, so when it hits the sample, it's about like 5 to 10 to 5 or 1 times 10 to 6 positron per second. And it's very bright. And it gives a very bright pattern as well. And then like in normal read, if you do diffraction using silicon single crystal, you see a lot of Kikuchi lines and stuff like that. But when you do this TREP, this kind of bulk related feature doesn't appear. And this is the photograph of this setup at B-Mine SPF A3 in KEK, which my colleague used for the measurement. And these are the data he got so it's a glancing angle dependent intensity change for different spots. And then he, by using the models we came up for the surface, he does a calculation, and the one most hit close was what we call this bitriangular structure. So it's basically a triangular structure or hexagonal lattice with a add atom in this form. We call it bitriangular structure. And our theory colleague find an interesting electronic structure in this kind of bitriangular structure. So probably some of you have heard about kagome lattice. So kagome means the basket weave pattern, and kagome is actually Japanese. And the lattice was originally invented to study ferromagnetism by theorists. So it's like a toy model for theorists. Interesting thing is that in honeycomb lattice, like graphene, it shows only direct cone, but this kind of kagome lattice, you have a flat band, which there's no energy change across the K space, which gives a very high density of states. And as some may know that this kind of high density of state, when it's tuned to Fermi level, it can give ferromagnetism or even superconductivity. Recent twisted graphene bilayer height is also considered to be a flat band given by the twisted, the smaller layers. And what my colleague found out was that so this is sort of intuitively understanding, it's all mathematics, but intuitively, if you sort of change this Kagome lattice in this arrow direction, then you can find the triangular lattice. And here in triangular lattice, you don't find any flat band, but if you add an atom here, then this part was could be a sort of truncated Kagome lattice. And then this kind of bitriangular lattice, when this position is tuned, it gives a flat band. So compared to Kagome lattice, which is perfectly flat, this kind of bitriangular lattice have a thickness. And this is actually an important point, like a buckled honeycomb lattice, like silicene or germanium. So depending on the height of this added atom, the position of this flat band in energy can be also tuned, which is the liberty which you did not have for Kagome lattice. And so this paper, this is purely sort of mathematic, not even DFT calculation. It's published in PRB. And we find that, so lead, Kagome, or checkerboard lattices are the kind of classic lattices used to study these kind of flat bands. But we find that with these kind of add atoms, with a structure with this kind of add atoms and with this kind of thickness, you can also find this flat band, which the origin, you can go back to the original leap or Kagome or checkerboard lattices. So we find a new group of structures which can have flat band material in its freestanding form. And then it will give us more chance to meet such kind of material. So we were very excited. Then the next question is what happens when it's placed on the substrate. So it's difficult to have freestanding forms of this kind of 2D crystals. And then what we have for 2D germanium on zirconium diborite, it is a germanium bitriangular lattice on zirconium diborite. So what happens when it's placed on the substrate? So here the left side is the optimized structure we get by DFT calculation, and the calculated band structure is given in this kind of orange or blue circles, which is related to germanium PZ, which is this orange ones. And then in the background for the panel C and D is the same what we measured at the synchrotron facility with APIS for this surface. So at endpoint of this lattice, we see sort of Derek cone-like feature, and also there's a kind of dispersing band along the Fermi level, and we see some kind of feature which is related to the very thin layer of metallic film. And then, so our understanding is that, so this is the very simple tight binding model and band structure for the simplified freestanding bitriangular lattice. So it's just the mathematics. And you see that the flat band, the red one, is at the top energy of all the bands. And then, so this is the freestanding case. And then we did with DFT calculation for the freestanding germanium bitriangular lattice with a lattice constant, what we have from the experiment. And then the bands, because it's hybridized with each other, it forms a band like this. And so originally flat bands are split into pieces, but the lower band looks quite similar in shape, although it's also sort of hybridized with the other orbitals. And then when we put this material on zirconium diboride in the supercomputer, and then we see that these red bands sort of shift down, and which comes close to this Fermi level. So what we see at the Fermi level, which is also dispersing when we see the experimental data, is originally a flat band, but now it's more sort of modified. So we call it nearly flat band. And then the part of this flat band goes deeper, close to the gamma point. And well, this one looks totally flat. And then the bottom band, which was highlighted as a blue, is sort of keeps the shape like this. And then this kind of shift was also understood by using the calculation by comparing the Millikan charge, well, per germanium atom. And it seems that when we place this germanium layer on zirconium diboride, there's a charge transfer from zirconium diboride to germanium layer. And that induces such kind of energy shift of the bands. And which is understandable because in zirconium diboride, this kind of boron honeycomb layer is stabilized by electron transfer from the metallic layer. And since zirconium diboride layer at the surface is zirconium terminated and it doesn't have boron layer on the top, this kind of charge transfer is happening when it have this kind of 2D layers. And actually, we believe such kind of situation makes this zirconium diboride as a material why we do not see any bare zirconium diboride, but always see well, silicon or germanium layer on top with a very controlled number of atoms. So I think it's about, so my story is about over. And with this, I would like to thank collaboration for with Dr. Fukaya, who is a scientist in Japan Atomic Energy Association. And he did all the trapped measurement at slow positron facility. He goes there like every 2 months or so and do the measurement alone, and also the modeling and calculation later on. And also I would like to thank Professor Ozaki's group at ISSP, Institute for Solid State Physics in the University of Tokyo, who did the first principles calculation with his postdocs. So Professor Ozaki is a graduate of our institute, and he develops OpenMX code, which is an open code for first principles calculation. And the rest is a collaborator who are specialized in superneutron radiation facility measurements, doing RPES and core level spectroscopies in UV SOAR and also photon factory. And I would also like to acknowledge the funding support from Japan Society for Promotion of Science for Kakenhi Grant. And so these are our recent publication again. So if you're interested, please take a look into these papers. So since last year, we had a 50% off for open access fee in American Physical Society because it was celebrating 50 years anniversary for physical review journals. I try to keep a lot of journals open access. So I think you can access very easily from home as well. With this, I would like to thank you for your attention. This is how we observed in our institute. So thank you very much.
Mittal sir, you're muted.
Thank you, Professor Yukiko Yamada. What a fascinating talk. It was so interesting that half an hour, just I looked, it is started. So it was good, very interesting talk. So any questions from the panel?
Dr. Takamura, I would like to ask, how stable are these flat band materials? What I mean to ask is, if I try to dope something into such material, will the flat band remain, or it'll, like, I feel it will get distorted, but how flat it will remain?
So doping is the thing we want to try right now. And for example, the first thing I would be interested in is to add like hydrogen. So when we terminate or when we add hydrogen as an add atom in the system, how these flat band position will change. Probably doing calculation is easier than doing experiment, but we can do both. But we the answer is we don't know yet. And and what we are doing right now is that all these results I've showed you today is at room temperature, and we have an interesting result at low temperature. So we're now trying to understand that. And probably, so doping comes later.
Okay. How low the temperature?
Pardon? At the temperature. Well, we see some interesting phase transition around, well, not so low,
Okay.
but some of my collaborator have also millikelvin SDM. So we can also go to very low temperature.
Thank you so much.
Any other questions from the panel?
Yes, sir. May I ask one?
Yes.
Yeah,
Okay.
ma'am, I wanted to know about its industrial application as we are comparing it with graphene, the silicene. So what are the industrial aspect or application of these material? Could you explain a bit?
So like Toyota Central Research Lab, they have a lot of work on silicene. And I think originally they were interested in such kind of material for lithium-ion battery electrodes, because compared to carbon, silicon can have more lithium. But nowadays, they're interested to have a very controlled thickness of silicon thin film, which can be used in a device. So that comes to the interesting part of application. But personally, the silicene material we're making right now is very easily oxidized in air. So it has to be encapsulated, which we have already done with hexagonal bond nitride. But also this kind of thin film has to be on the thin dielectrics. So, and probably the option will be kind of hexagonal bond nitride. So I think there's a lot of technical challenges to actually apply it to devices.
Yes, ma'am. Thank you.
Okay, Mittal sir, I would like to comment. Okay, so thank you, Takamura-san, for updating us about your recent work on silicene materials. It's very nice, and it's to see that it experiment and theory, it matches very well for all the cases. And I would like to share to the audience that Takamura-san first paper on silicene, it's published in PRL, it's open access journal, and within 11 years it got 1,200, more than 1,200 citations. So every month that paper is getting more than 100 citations. So it's well recognized by the all across the world. So thank you, Takamura-san, again.
Thank you.
To listen to you.
Any other question, or I will take from the question answer from the audience. So one question is from Abhirami R. She's asking them, can you tell me why X-ray spectra take a long time to obtain, and also why it fails to detect hydrogen and helium?
So long, I don't understand what long time means. Is there
this just mention the how long does it take to take this XPS spectra?
It doesn't take very long.
Period of time means how much?
How long it takes?
Yes.
Measurement time is not that long. I mean, the whole setting takes longer in a synchrotron radiation measurement.
No, and for this silicon or germanium film, it is taking the same time as the other materials, or you have to do it longer or shorter?
No, it's the same.
It's the same
Yeah,
method, same
it's
time.
very easy. Yeah, yes.
Okay.
Yes,
So,
especially if you do it in synchrotron, it's very short.
okay. Ma'am, I have two questions. One is why have you studied on only the zirconium boride or some other surface also?
Yeah, we're now studying on other chalcogenides, which are lattice matching to silicene and germanium. So my students are, and chalcogenides, it's difficult to get large substrate. So my students are first growing chalcogenide thin films, single crystalline way on, silicon or germanium. And then we deposit silicon or germanium or even tin and trying to find out what kind of two-dimensional structure it will form. But that's another story. But before going to that step, my student accidentally found a new polymorph of chalcogenides, and that's also another interesting result we have right now.
And second is positron facility in Japan. Can anyone avail that, or you have to be Japanese or some collaboration or something?
I think they accept proposals. So you can go to their home webpage. There's an English webpage, and I think there's an application. And I have not personally applied myself. Always my colleague applies. So, but he is always writing a proposal, and then it's reviewed, and then he gets beam time. So I think it also works for other people as well. And from him, I heard that there's also there's only another group in Germany who are doing similar kind of measurements. So only two places in the world, I think. But it's very powerful method for 2D materials.
Yes, of course. Yes, it seems that it is very powerful and surface sensitive than the read technique. Yes, that seems to be better. But can we use this technique for in epitaxial growth, like Reed is doing? Now epitaxy, they are using Reed technique. But can this positron facility also used in place of Reed in case of epitaxy?
I don't know if they do it real time, but my colleague also do deposition in this chamber. So that's possible, but I don't know if he does it in situ.
Okay.
Am I answering your question?
I think so. Because just this was hypothetical that it can be used, because in epitaxy we need very high sensitive surface measurements, because there the film is very thin. So maybe it may be used or it may be not. It depends on how much you get the structure. So the characterization is how much strong. So maybe it's okay.
I know that he does growth in this chamber, but
yes,
I don't know the configuration. So I'm not sure if you can do in situ measurement or not. That I have to ask him.
Thank you very much. Any other question?
Yeah,
one question
yes,
is
Dr. Mittal, Professor Yamada, really wonderful talk. People generally say that the silicene is the replacement of the graphene. So due to this structure, due to the atomic layer, so do you think that in electronic industry, this silicene is going to revolutionize the silicon market once again?
Well, silicene right now is not having the property which is expected for its freestanding form. But I'm interested in having this kind of silicon layer in a very controlled thickness in that sense. But probably electronic industry is more interested in having their silicon-like counterpart in a very decisive thickness. So in that sense, this kind of spontaneous formation of a 2D layer itself, so the formation mechanism, I would say, is more interesting for them rather than the material silicene itself.
Okay. There is a question in the somebody has asked, Abhirami has asked that why we cannot do the XPS of the hydrogen and the helium. See, the hydrogen has the only one s electron, so it is very difficult to detect this is the core or this is the valence electron, because from XPS you are basically looking for the core electron, and that's why using the XPS either hydrogen or the helium detection is almost impossible. Another issue is with the XPS is that it required ultra high vacuum. So helium is not in the solid form. So again, due to that reason, helium detection is impossible, and due to the only 2 electron, it is very difficult. Cross section is very small. So it is very difficult to distinguish between the core electron and the valence electron. And that's why XPS is not able to detect either hydrogen or the helium. I hope this will give you a satisfactory answer for that. That's what basically the limitation of the XPS. Thank you.
So one question is from Dr. Kalavati Seni to Dr. This is how zirconium boride 0001 differs from zirconium boride 001.
So it's the same. So 3-digit is for Miller indices and 4-digit is for Miller-Robe indices. For hexagonal system, it's useful to have 4 digits rather than the 3, so that it can give the same or equivalent direction or equivalent plane in the combination of same numbers. So I just taught that actually in my solid state physics class last week.
So any other questions? So thank you, Dr. Yukiko Yamada.
Thank you.
And it is highly we learned a lot from your lecture about what is the silicene and about these materials. Thank you very much again from me and also from the MIT University to giving this fascinating lecture. Okay.
Hope to see you all in Japan in the near future.
Maybe.
Let's stay safe and healthy.
Yeah. Thank you.
Thank you.
Thank you.
We will try to contact you for the student exchange program
please.
under India and the JSPS scheme.
Yes, please.
And we'll be explore the MOU between ENT and your institution if feasible.
Yes.
Yeah.
We welcome that.
Yeah. Thank you.
Thank you. Bye-bye.
Thank you, madam. Bye. So, Pooja, our next.
Before that, IT support, please give rights to Dr. Shambhunath Bera as please make him the co-host. Pooja, please proceed.
Our next speaker of this technical section is Professor B.R. Mehta. Professor Bodhiraj Mehta is currently Dean Research and Development and Shumbaga Chair Professor at Indian Institute of Technology, Delhi, New Delhi. He did his PhD from IIT Delhi. He has worked as visiting scientist and professor at many institutions across the globe. His areas of interest includes 2D materials and 2D, 3D interfaces for thermoelectric, solar cell, photoelectrochemical, and gas sensor devices. He is the recipient of MRSI Medal, Material Research Society of India, DAD Fellowship, Marie Curie International Fellowship, Material Science Society Annual Prize. He is on the editorial board of Journal of Nanoscience and Nanotechnology and has many publications to his credit. One of his project, Nano Switch, has been elected by European Commission as a success story project. Today, he is going to enlighten us on the application of 2D materials and devices. On this note, I welcome Professor B.R. Mehta on this virtual platform. Sir, you have 45 minutes followed by 10 minutes of question and answer session. I request you to please conclude the talk in the timeline. Over to you, sir.
Welcome, Professor Mehta.
Thank
It's
you.
a pleasure
Thank
to
you.
have you in our platform.
Thank you very much. So can you see my slides?
Yeah.
Yes, sir. You can see.
May I start?
Yes.
Thank you very much. So let me first mention two things. One, I am thankful to MIT University, especially the organizers of this meeting, for giving me this opportunity to discuss some of the recent results which we have achieved in this area. And second thing is, although I have done many experiments involving ion beam damage earlier, but today I will prefer to discuss on these 2D, 3D interfaces and the studies which we have carried out, because these are recent results, very recent results. And also these are in line with the first presentation, which you have, very nice presentation, which was there. That was also on a similar area. So what I'm speaking is that what is the nature of the basic idea, of the central idea of the presentation today is how to study 2D, 3D interfaces. Okay, because these 2D, 3D interfaces, you know, they affect the performance of the devices which are based on the 2D materials, and hence investigating these interfaces is very, very important. I think this audience, this slide is not important. What I'm showing here is that interfaces are an integral part of semiconductor devices. You can see a solar cell, EN junction. In fact, there are many other. There is a contact between metal contact with a semiconductor, bottom contact with another semiconductor, and a junction between two semiconductors, PN junction or heterojunction. Different types of junctions are used in solar cell. To have a thermoelectric device, also there are interfaces between two different materials, most of the time N and P type. Photoelectrochemical device, random access memory application, light emitting diodes, all semiconductor devices, in fact, somewhere or the other, the interface will come. And the interfaces is between semiconductors which have different crystal structure, different energy band diagram, different electrical properties. You can see that this leads to a lot of interesting complexities in interfaces. Not only interface is the most important part because it controls the transport and thus the device performance, but also people who work in semiconductor devices, they know it very well, that it's very difficult and very complex to, and from research point of view, it becomes very interesting to investigate interfaces, how interface can be studied. And as I was discussing, the interfaces between 2D and 3D, between two materials or different crystal structure, for example. So you have electrical contact between gold and gallium arsenide. You have one material, gallium arsenide, another material. So two different atoms sitting at the interface, they will interdiffuse at any temperature above close to room temperature, or when you're fabricating it, the junction will undergo higher temperatures. So interdiffusion is an integral part of interfaces. So that means there will be a layer in between the two materials which will have different properties. And most of the time uncontrolled. It becomes very difficult to control the spectrum. Materials having different crystal structures. Here, interdiffusions are occurring because the two materials are having different composition, different atoms, so they will diffuse. Now, second thing, if two materials have different crystal structures, one material having different atomic arrangement, another material having different atomic arrangement, will be defects at the interface. How this crystal structure aligns with this crystal structure, this will lead to defect. And this is very well known in three-dimensional solid-state devices, solid-state physics. And you know that this effect is called Fermi level pinning, because normal p-n junction, when we teach students in semiconductor physics course, we say p and n junction, when you align them, the Fermi levels align. But the presence of this higher concentration, large concentration of defects at the interface leads to a phenomena which is called Fermi level pinning. So the defects, the presence of the defects, the nature of the defects, that controls the Fermi level at the interface. The Fermi level is no more controlled by P and N properties of the P and N type, but the defects will start controlling those properties. Now, this is nothing to do with 2D materials. We are discussing three-dimensional materials. So you can see that there are complexities in three-dimensional material itself. Now we come to two-dimensional materials. If one of the material, let's say, is two-dimensional, metal graphene interface, for example, which we will discuss later on. Okay, or I will discuss interface between moly sulfide and bismuth telluride, for example, for thermoelectric material, where one of the semiconductor is 2D material. And you know that 2D, so this is a normal 3D junction which we are discussing, but when you have a metal 2D contact, it can happen that there is a van der Waals gap between them. Then the two materials are not even bonded to each other. So you can see that this is a big difference from the 3D material, van der Waals gap between 2D material and 3D material. Or if there is a covalent bonding, there are materials where the bonding can also take place. So you can see that this will also influence the nature of two-dimensional and three-dimensional interface. So, but what I'm discussing here is something even more important. Compare what is the thickness of the 2D materials, comparable 2D material thickness at the interface. For example, this interface layer which we are discussing, or the defects which will be present at the interface. There is a defect layer will be formed in between the P and N layer. Now we have another complication because the thickness of the 2D material is very small. And how this influences the characterization and how it influences the physics of these junctions is a very, very important question. So we will not have answers to these questions at the end of the discussion. What I'm going to do is I'm going to highlight these questions, that how these questions are very, very important. And we must look into this. We must focus our research. So the central idea of this talk is not to present answers, but to raise important questions and to highlight these questions. Okay. So what we have been, so this is very fascinating topic. And in our lab for the last 2 or 3 years, we have been working on this topic, this direction. 2D, 3D junctions. So it's for a solar cell. In fact, this is an example I'm not discussing today. This is the first example we took where we developed a single nanorod junction between, that means within the nanorod, there was half of the nanorod was cadmium sulfide and the other half was copper sulfide. And so it was very, very interesting and very challenging. How do you characterize this kind of interface within the nanorod, half of the nanorod literally? And this is also, I normally use it to teach students, but because of the lack of time today, I will not discuss it. Then we also worked on graphene silicon junctions. So in fact, this was a project which was funded by BEL, and they wanted to understand that can we replace the silver contact on silicon, which are used in commercial silicon cells. Can that be replaced? That is important, that adds to the cost of the solar cell today. If you are to reduce the cost, this is one of the components. Silver you can remove and reduce the cost slightly. So can it be replaced, silver, can it be replaced by carbon materials like graphene because it is transparent and conductive? So that was the starting point, and we investigated graphene silicon junctions. In fact, so this is the first example which I will use in the present talk. Then another layer, another system which we investigated. In fact, this is a topic of one of my PhD student, intermediate semiconductor. Intermediate semiconductor is that within a semiconductor, you can introduce a intermediate band so that its optical absorption or photon absorption is enhanced and it takes place at a larger energy range. So that means one photon will be absorbed with electron transmission from the valence band to the intermediate band, and another photon or different energy can take this electron from the intermediate band to the conduction band. That's the idea. And you know that, so what we thought, because moly sulfide has a smaller band gap, 2D material, zinc sulfide has a wider band gap material, can we form an interface between moly sulfide and zinc sulfide? And then can this act like a intermediate semiconductor combination? And it is also interesting from the point of view because the properties of moly sulfide can be changed by controlling the thickness, by controlling the number of layers. But here also, what is most important is how does the bands of moly sulfide aligns with the bands of zinc sulfide. And that is why we choose this to understand this moly sulfide zinc sulfide junction. Cadmium sulfide and copper zinc tin sulfide. This is a solar cell material. This is not a 2D, 3D material, but it is a bulk material. But here what happens is because of the composition, because you can see that there are a large number of materials, cadmium, sulfur, copper, zinc, tin. And sometimes you have sulfur and you have selenium also. So the large number of elements present results into the presence of secondary phase, emergence of secondary phases at the interface. And this can...
Sir, you are on mute.
I'm sorry, sir.
Sorry. Okay, sir. Thank you.
I'm sorry. So what I was telling was that the presence of these secondary phases influence the cadmium sulfide and CZTS interfaces because secondary phases like zinc telluride, zinc sulfide, and tin sulfide present at the interface can influence the properties. So we did some experiments on understanding the role of these secondary phases at the interface. But this is not what I'm going to discuss. I will take the first example of graphene and silicon. And then the second example we will take will be of thermoelectric material. Thermoelectric material, as I will discuss in more detail later, to improve the thermoelectric properties, what we have to do is we have to increase the phonon scattering, okay, without decreasing the electron scattering. So there we utilize the presence of 2D materials to do this, okay? And I will explain to later. So we investigated bismuth telluride interfaces with graphene, bismuth telluride interfaces with moly sulfide, and bismuth and moly sulfide interfaces with antimony telluride. So, and maybe one or two of these interfaces we will take up in this discussion. So just to give you an idea to the students, what we have done is we have used scanning probe techniques to investigate these junctions. And I will give you a slightly brief introduction. Two techniques which we have used: conducting atomic force microscopy and Kelvin probe force microscopy. Conducting atomic force microscopy is similar. It's like atomic force microscope. Both are based on atomic force microscopes. You have a conducting sample, let's say, and you have a tip. Normally, FM tip is not conducting, but when you're doing conducting atomic force microscope, you can deposit gold on this, or you can get gold-coated AFM tips from the commercial market. And so the tip is conducting, and you apply a voltage between the tip and the sample, and you measure the current. That's how. So at the local point. So normally, this is how it works. Because of the one contact is, you can see, is very large area. You can see this part of my slide. You can see it here. This contact is very large. The top contact is only equal, the area of the top contact is only the tip area, or 2 or 3 times the tip area. The top area is 10 to 50 nanometer, bottom area is very large. So this difference in the area of the two contacts makes it different, that most of the current paths or the electrons will go through like this, and that's how they will go. And what happens is this part of the device has larger resistance and compared. So what you are investigating, it's called spreading resistance mode. So what you are investigating, you can see that tip, you are investigating only this part of the sample. Okay, and this part, the area or the depth is 2 or 3 times or 4 times the tip dimensions. So if the tip dimension is 5 nanometer, what you're investigating is 15 nanometer or 20 nanometer area and 20 nanometer depth. That part of the sample is being investigated. So in scanning probe techniques, you can go from one point to the other and measure the electrical properties at nanoscale. That is what is important. So nanoscale variation in electrical conductivity, for example, can be investigated. Or nanoscale variation in the current, for example, in solar cell, you can investigate how the current is different from different points. And the other technique which I'm going to discuss is Kelvin probe force microscope. Okay, Kelvin force microscopy, if you have to explain, it is similar to a contact between a tip, this is tip, and this is the surface which you're investigating, semiconductor surface and the tip. This is the, the work function of the tip is the difference between the Fermi level and the vacuum level. So this is the work function of the tip. This is the work function of the semiconductor, what you are investigating. This is a standard material, so we know its work function. Okay, but when you make this junction, you can, so there is a gap. You can see that this is the Fermi level of the tip and the sample is aligned. And this potential difference, contact potential difference, CPD, which is called, this is equal to the difference in the work function of the tip and the sample. If you know the work function of the tip, it's a standard platinum material, you can find out the work function of the sample surface. And as already, and of course, this contact potential difference can be negative or positive if the work function of the tip is less or more than that of the sample surface. And we can measure its magnitude. But the good thing, and the magnitude, the resolution, the voltage resolution of a Kelvin probe force microscope is around few milli-electron volt. So you can see that. So it's very useful for semiconductor devices. If you can measure, so what we are saying is we can measure the work function of a semiconductor surface with a resolution of few milli-electron volts. Okay, and the spatial resolution, which I already told you, is already nanoscale. So we can, in fact, measure the work function of the semiconductor surface from point to point. You can generate a map of the work function map or contact surface potential map of your surface. Can be done with a Kelvin probe force microscopy. And this is how the Kelvin probe force microscopy is actually done. This is how it is actually done. And this is the, so what you do is, to keep the discussion simple, is you apply a AC voltage and the DC voltage together. Okay, contact potential. So, and when and you keep on modulating the DC voltage, when your DC voltage is equal to the contact potential difference, okay, then the force modulation with respect to Z, delta F by delta Z is equal to 0. Omega is the frequency which we have applied, AC signal. So it becomes a very convenient method of making a measurement. You will keep on changing your DC voltage, and when the gradient of the force on the tip is 0 or negligible, that DC voltage is your contact potential difference. So we know the contact potential difference. Because we know the work function of the tip, we will know the work function of the semiconductor. Okay, so just a minute. In fact, I decided that I will show you the first example, another example, because that this example helps the students actually sitting in the. So I will take one more example, okay, than I planned earlier. So just give me. Okay. All right, so this example is the cadmium sulfide, copper sulfide, single nanorod junction, which I was telling you. Just I will take 5 minutes describing this because this helps us to know how Kelvin probe force microscopy will work. Okay, but here we are not investigating 2D interfaces, but it is a good example. So you can see that this is the AFM, this is a surface potential map, which we can generate. So this is a cadmium sulfide nanorod. Half of it is can you hear me?
Yes, sir.
Yes, sir, we can hear.
Yes, sir. Yes, sir. We are able to hear.
Okay. So this is a cadmium sulfide copper sulfide junction. This is the contact pressure difference, surface potential difference under dark conditions. And this is the surface potential difference under light conditions. You can see that there's a large difference. Okay, this you can see this is a spatial resolution in the X and Y direction. The Z resolution, because here it is a color map, the color contrast shows you the potential difference, surface potential difference is changing from point to point, or the contact potential or the work function is changing from point to point. What we can do is, how do we analyze this junction, this kind of interface? Okay, you can see that if this map you take, and because what Kelvin probe force microscopy has done is it has measured the work function at different points. So the computer actually knows the work function value at different XY values. Okay, so you count those points and put the number of points at different work function values. So you have here in the x-axis is the work function and y-axis is the number of points. That means at this point, for example, if I take, there are about 1,000 points in this map, which has a work function around 4.0. That's how the contrast is changing, and you can give different colors. And you can see actually this image has 3 types of work function, although there is some sort of distribution, but there are 3 values. So you will see later, one of them is cadmium sulfide work function, other is copper sulfide work function, and the third function is the background, which is the indium tin oxide here. Okay, so this way you can generate a map of the work function map, and then you can get the information about this. Red is ITO, the blue is cadmium sulfide, and the green is copper sulfide. In fact, the ITO is not very important. We should focus our discussion to this. So you can see it here. So what I can do is, in fact, I can go back because I know which point now here, which XY point has what value of work function. I can put, with the help of computer graphics, I can put the color into this map so that now I see that which points are green. Green means they have a work function this much. Red points, they have a work function this much. And these points have a work function this much. This work function belongs to ITO. This work function is, I think, cadmium sulfide, and this work function is copper sulfide. You can see now, you can see the junction is appearing now. In the topography, if you topography image, there's no junction, but when you do Kelvin probe force microscopy image, you have a junction. Interesting thing happens when you shine light on this junction. You shine this light. This part is not important. I already told you, forget about the indium tin oxide part. The cadmium sulfide copper sulfide part, a new peak is appearing between cadmium sulfide. So that means there's a part in this map which now has a work function which is different from cadmium sulfide and copper sulfide. Where are those points? If we ask the question, those points are physically located between cadmium sulfide and copper sulfide. What is the work function value? Work function value is also in between. So what does it mean? This is the interface which has formed between cadmium sulfide and copper sulfide. When you shine light, then you can resolve the work function. And now I can in fact measure the thickness of this interface. It's around 10 nanometer in this case. So this is the way Kelvin probe force microscopy works. But later on, I'm going to quickly shift And you will see that this is not the way we will utilize Kelvin probe force microscope. We will use Kelvin probe force microscopy to investigate the interfaces in a different way. Let's take that examples. Graphene, silicon junction. So silicon dioxide, and graphene. And as I mentioned, we were doing this experiment with BHEL with silicon PN solar cell, which was untextured. Okay, on planars. Normally the solar cells are untextured because we wanted to do these experiments with using graphene. So they specially made the cells for us, which didn't have the texturing. So what we have a silver contact here, and we deposited graphene layer 1 centimeter by 1 centimeter, and then we investigated the IV characteristic under dark. This is the light IV characteristic. You can see when we go from silicon to graphene silicon, there is small change in the open circuit voltage, but large change in the current. And when you go to, because this was not having anti-reflection coating, we deposited silicon dioxide over graphene. So there are two cases, silicon, and then you go to deposit graphene, and then you deposit silicon dioxide. What is important is you can see that if you see the change in the current, this is the change in the current on going from silicon to graphene silicon. But change in the reflectance, this is the optical effect, and this is the electrical effect. You can see there's no change in the optical properties because when you put graphene, it's transparent. It will not even affect the reflectance of the solar cell. So optically, the cell has not changed. But electrically, the cell has changed, the current has changed. So that gave us an idea that we must investigate this junction because it's electrically more important, this junction. So we must investigate. So that is why we made special cells. So we had took N-type silicon now. There's no solar cell now. So you just have N-type silicon, and we deposited graphene on top, and this junction is there. And we investigated this junction using Kelvin probe force microscopy. And that, in fact, is the topic of today's discussion. So this is, you can say that this is the junction. This is a model junction. So you have a silicon. You have a silicon here, and you have graphene, and this is the conducting atomic force microscopy tip. And we have deposited silicon dioxide here because the thickness of the graphene is so small. If you don't deposit silicon dioxide, then this aluminum will puncture through graphene and it will touch silicon. So it is always when you're working with 2D material and you want to take electrical contact, you normally do this kind of deposit silicon dioxide and then deposit graphene over there. And so that this helps you to take electrical contact. So using conducting atomic force microscope, we can do dark measurement. You are here, there's no current. When you don't shine light on it, no current in the solar cell. When you shine light, we are somewhere here. You can measure at a particular value the voltage. You can measure the current. So you can see from dark to current, dark to light condition, there is a change. So this actually a small solar cell has been formed. Actually, what it means is, what is solar cell? But a graphene silicon itself is a solar cell. Weak solar cell. We want to investigate it. Okay. So now this is a very important slide for my presentation because this is a slightly different way we are utilizing Kelvin probe force microscopy. You can understand Kelvin probe force microscopy will investigate the top surface. You can get the work function map of the top surface. That's what we did in cadmium sulfide and copper sulfide. Top surface. It is a surface which is being investigated. And we are not interested in investigating the top surface. We are interested in investigating the junction between silicon and graphene and not the top surface. So what we did measurements under two configurations. One we call as the surface measurement. This is surface measurement. You can see this is a normal measurement. You apply a voltage, AC voltage and DC voltage, which you do in Kelvin force microscopy between the tip and of course in the back contact here. And actually, so you're applying between this and the top surface. AFM tip and the top surface. That's how now KPF measurements is done, and you can do work function or surface potential map of the top surface. What we also did is we did what we call as a junction mode. Here you can see that the voltages, AC and DC voltages, are being applied to the back contact. So the voltage is coming through silicon through the interface and then to the graphene. Okay, so you can see that the interface is coming into the picture here. Okay, so you do a generate voltage map or work function map of this layer, work function map of this configuration. You will see that in one of them, the interface is additional effect. If I subtract these work function maps of these two images or the two cases, subtract them, everything else is subtracted out. And what is left is the effect of electric field present at the interface on the contact potential difference. Okay, and because we have a map, so you have a electric field map of the junction at different X and Y points. Just to give you, let's understand it more. You remember the histograms which we have plotted. So this is the histogram which we have. So what you actually get is you get this kind of images. You get this kind of images. From each of these images, you can generate a histogram. Okay, so this is the histogram generated in the junction mode. This is the histogram generated in the surface mode. You can see that the voltages are very different. Surface potential is 280. Here the surface potential is 90. Why it is different? In dark, there's no difference. Dark, both of them gives the same value, but in the junction, they are different. So you can see that in the light and here also there. So in fact, this difference is coming due to the voltage which is there in the junction. Actually, it's very close to the open circuit voltage. Okay, so open circuit voltage. And in fact, what we did is you can see that this, so when you're doing the measurement, you can do dark measurement, light measurement, dark measurement, and light measurement. In the surface mode, you can see that when you're in dark, the voltage is more. When you are under light, it is slightly less. Whereas in case of surface mode, dark is less and the light voltage is more. So very drastic changes have taken place. So this is the light kPFM image of the surface mode. This is the light kPFM image of the junction mode. Image means we have the values at each X and Y point. You can subtract those values and you can get this image. This difference image is what? It is the open circuit voltage image or the voltage present between graphene and silicon at different X and Y points. Okay. So this kind of image we can generate. And again, this image is the difference image. And this image, again, you can plot the histogram. Number of events, open circuit voltage. So 190, that's the average value. But you can see there are certain points where the voltage is slightly less. This is the voltage, this is the open circuit voltage peak. But there is another peak which is having less number of points. Number of points are less, but the voltage is slightly less. In fact, I can go back just like in the cadmium sulfide case, I give red and green and blue points. I can give different colors to these points. Because I exactly know where these points are there in this image. Okay, you can see that. Now I've given the white color to those points where the voltage was less. And we know we can relate it with the atomic force microscopy picture. And you can see that this difference or the weak points which are there, they were the wrinkled boundaries in graphene. When you deposit graphene, it's not smooth. Many places it gets wrinkled. Wherever the wrinkle is, the number of layers are different and the electrical properties are different. Or when you're transferring graphene, we normally use PMMA. That's required in the transformer process. And normally you have to remove the PMMA. But many times, the small particles of PMMA are left on graphene and they change its properties. And you can see that the presence of these PMMA particles also can change your voltage. So what I'm trying to say in this example is the Kelvin probe force microscopy can be used to understand how the defects and these impurities can affect the interface between graphene and silicon. Okay, and then you can try to rectify the error. But let's go to the second part, which is even more interesting. So we are now investigating what bismuth telluride, molysulfide, and antimony telluride molysulfide 2D interfaces for thermoelectric material. So as I mentioned earlier, thermoelectric material are defined by a figure of merit. This figure of merit is called ZT, is the figure of merit. And ZT depends upon the Seebeck coefficient. This is important for thermoelectric material. How much temperature difference will give you how much voltage. So Seebeck coefficient is more. So if the material has a large Seebeck coefficient, it will have large figure of merit. Then it depends directly on the conductivity of the material. Higher the conductivity, higher is the ZT. And it is inversely proportional to thermal conductivity. Higher is the thermal conductivity, lesser is ZT. So electrical conductivity is useful, Seebeck coefficient is useful, thermal conductivity should be controlled. Okay, thermal conductivity should be controlled. So this is important. How do we increase the electrical conductivity, or how do we keep the thermal conductivity under control without sacrificing the electrical conductivity, without affecting the electrical conductivity? So what you have to do is you have to introduce scattering centers for phonons. So you have to have something in your material which will scatter phonons, but which will not scatter electrons. Okay, so that whatever you do, electron scattering is not affected, electron density is not affected, so that the conductivity remains unaffected. Electrical conductivity remains unaffected. Thermal conductivity, because you also know that thermal conductivity has two parts, electrical part and the phononic part. We cannot do anything to the electronic part, because if you want to decrease the electronic thermal conductivity, that will also change the electrical conductivity. So that is kept unaffected. What you have to do is you have to change, you have to reduce the phononic thermal conductivity. And that is why phonon scattering has to be controlled. So what is proposed is that you can introduce two-dimensional interfaces in a thermoelectric materials. Like you add molysulfide or graphene. The thickness of graphene or molysulfide is very small. It's a few nanometer. Electrons can tunnel through this thickness. Whereas phonon, it's of the order of the scattering length for phonon. So phonon will get scattered. Electrons will zip through the 2D material. So electrons will not scattered, phonons will. So that's the idea. Many people have utilized this idea to increase the figure of merit of thermoelectric material, and they have been successful. So just this is one of the work of one of my students. You can see that what we have here is, it's not a 2D, 3D interface as such, but it's a bulk material. Okay, it's a bulk material prepared by, it's like a pellet of molysulfide and antimony telluride, or bismuth telluride also it can be done. And in fact, we have done both, but I'm just showing you the results of antimony telluride. So it's a pellet made of antimony telluride, which has 2 or 3% of 2D flakes of molysulfide. So when you do this, so in fact, the results are, you can see that this black line is for bismuth telluride, and this red line is for bismuth telluride having some very small percentage of molysulfide. This line is for antimony telluride, and this line is for composite antimony telluride, molysulfide. And what we are measuring is electrical conductivity as a function of temperature. What this shows, when you add molysulfide 2D layers, the electrical conductivity of bismuth telluride decreases, and electrical conductivity of antimony telluride increases. You know that for a figure of merit, we want better electrical conductivity. So this is not from electrical conductivity point of view, bismuth telluride result was not good, antimony telluride result was better. We made the thermal conductivity now. Thermal conductivity, you can see in case of bismuth telluride, large decrease in the thermal conductivity on introduction of molysulfide. This is very good. When you have bismuth telluride, you add molysulfide, large decrease in the thermal conductivity. And in case of antimony telluride, no change in thermal conductivity. Then even in case of, this is Seebeck coefficient. In case of bismuth telluride, increase in the Seebeck coefficient is larger. In case of antimony telluride, the increase in the Seebeck coefficient is smaller. You can see that. each factor, 3 factors which are important for thermoelectric material: electrical conductivity, thermal conductivity, and Seebeck coefficient. They are getting affected in a different way. When you change the material from antimagnetite to bismutalite, what is the difference between them? One of them is N-type, another is P-type. So they form different types of interfaces with molysulfide. That's what I'm highlighting. That interface is very important. To answer these questions, what we have to do? You have to investigate this interface. Okay, so what we have done, you can see that from this, we prepared a model interface because we wanted to. So what we prepared, a thin film of antimagnetite or bismutalite, deposit a 2D material of molysulfide. And in fact, in this case, I will show you, now we can even change the thickness of molysulfide. You can go from 1 layer to 2 layers to 5 layers to 20 layers. And you can see that how the number of layers are affecting these properties. And now, because we want to investigate the interface, we will do the measurements in the 2 modes, in the surface mode and in the junction mode, and investigate this interface. What are the changes which are taking place in the interface which are affecting the thermoelectric properties, conductivity, Seebeck coefficient, and thermal conductivity in a different way? But before we go to the actual measurement, this is what I was discussing in the beginning. If you form a junction between antimagnetite and molysulfide, one of them is P, another is N material, and we can make these calculations. In fact, this is a good tutorial question for students. You make the calculation, what is the thickness of the depletion region depending upon the carrier concentration of a material. You can 10^13, the depletion region is around 7 to 8 micron. What is the carrier concentration? Sorry, what is the carrier concentration in bulk molysulfide? Around 10^17. So depletion region in bulk molysulfide is few micron. The thickness of molysulfide bulk is, let's say, 20 micron. Depletion region is 0.5 micron, no problem. But in 2D material, the electrical conductivity corresponds to 10^13. Depletion region is very large. Thickness of the material is smaller. That's what the question I was posing earlier. So in the bulk case, if you do these measurements in the surface mode, in the bulk mode, and this is the result you're getting. There's no difference in these measurements in the bulk case. Because in the bulk case, what is happening is you have P-type material, which is the antimagnetite. You have N-type material, which is molysulfide. This is the depletion region on one side, this is the depletion on the other side, no problem. And this is, you can see the charge or the carriers, which are the charges which are there on the depletion region on this side and the depletion region on this side. And that's the junction, how we are doing the measurement. This is the energy band diagram, the energy band of antimagnetite. This is the energy band of molysulfide. This is the Fermi level. This is the tip. What I'm measuring is this difference between the tip work function, Fermi level of the tip, and the Fermi level of the material. Whether I do the measurement here or I do the measurement here, work function, this line is same. Fermi level is aligned in the case of bulk. So these two measurements, when I do the measurements in 1 and 2 or 1 and 3, there is no difference. Surface and junction mode gives you the same result. But when my thickness, so this is the bulk, 20 nanometer. But then when I go to 40 nanometer, 20 nanometer, no difference. But when I only have 2-dimensional layer, bilayer, 2 layers of molysulfide, you can see there is a large gap. There's something happening between the bulk and the junction mode. If I have a monolayer, this gap is even more. What is happening is, you can see that now you can compare the bulk case and the 2-dimensional case. In the 2-dimensional case, the depletion region width, you can see required is this much. But the thickness of molysulfide is very small. You don't have enough molysulfide to support the complete charge which will flow onto from the other side. So what has to happen? This charge will get accumulated at the top surface. So the molysulfide, you have a charge on the top surface, which is called, calling it a surface charge accumulation. And this is what is changing the surface potential between the junction mode and the bulk mode. This is only one question. We have answered one question. We are able to characterize junction. We are able to characterize two-dimensional, three-dimensional junctions by utilizing Kelvin probe force microscopy in surface mode and junction mode, and then taking the difference of these two measurements. But the next question is even more important. How is this charge now affecting those thermoelectric properties? Okay, the presence of the charge, how is it affected? So it's again, those results are summarized here. You can see the thickness of molysulfide is 20 nanometer. There's no difference, but as the thickness reduces, the difference of the surface potential in surface mode and junction mode is getting increased. And what we know do is the macroscopic measurement. If bulk molysulfide and antimonitored, right? If you make the measurements, it is similar. It's a symmetric, nonlinear, ohmic kind of junction. But in two-dimensional molysulfide, the junction becomes non-ohmic, unsymmetric, and so there's a small change. How does this change affect the electronic thermoelectric thermoconductivity property is a next question which has to be investigated. But in order to answer this question, what we did is we are now investigating we've prepared multi-layer structures. So what you would say, what is this multi-layer structure is? This multi-layer structure, okay, this multi-layer structures has 20 layers of antimoniterite, having a thick, or 11 layers of antimoniterite, each having a thickness of 20 nanometer. Molysulfide having 10 nanometer, having 10 layers. So the total thickness of this is around 320 nanometer, and it has 11 layers of antimoniterite and around 10 layers of molysulfide. Now you can see, so now we are able to introduce 10 or 15, 10 or 11 interfaces in this material, okay? Because you want to introduce large number of these interfaces. You remember that composite, it has different interfaces, but they were not in a systematic way. These are the interfaces present. As the electrons and phonons move, they will go through these interfaces. Phonons should get scattered, electrons will not get scattered. That's the idea. So these are the cross-sectional TM picture. You can see the interfaces. This is 20 nanometer of antimoniterite and 10 nanometer of molysulfide. You can also see lattice fringes and so on here. You can see the change. So now in this case, this is the electrical conductivity. This is antimoniterite. This is antimoniterite with 5 layers of molysulfide, and okay, this is antimoniterite having 10 layers of molysulfide. You can see that there is a decrease in the electrical conductivity. And this is the Seebeck coefficient, and this is the figure of merit, which is the power factor. There's another figure of merit, how they are getting influenced by these interfaces. Okay. Is what we are investigating. So I think I'm running short of time. Can you tell me how much time, or I have already crossed?
Sir, time is already crossed, but you can finish in another 5 minutes.
5 minutes. Yes.
Okay. So I'm going to take 2 or 3 minutes. So you can see that
His video is frozen. Sir is disconnected.
I think sir is disconnected, ma'am.
Sir is around because his screen is coming, but probably the net issue is here.
slightly,
Yeah.
this is not favorable condition, but this decrease is not having that kind of effect which the decrease in thermal conductivity and increase in Seebeck coefficient. So you have to do compromise. Okay. So what is it resulting is, it's resulting in an increase of power factor from 2 to around 5. So this is a very large power factor in a 3-dimensional structure. In fact, one of the largest power factor which has been reported by the literature. So what it shows is, by introduction of these interfaces, one can improve the thermoconductivity, Seebeck coefficient, and of course, electrical conductivity is getting affected in a different way. And ZT and power factor, these are some of the values which are reported in literature. And you can see that this is our present work. So it's quite a good result. So So I will stop here. What I'm saying is that the conclusion of this talk, that nanoscale mapping of the 2D, 3D interfaces can be done using Kelvin force microscopy. And I forgot to mention that there are two advantages. Because you are doing two measurements and then you're taking a difference between them. Two readings and you take a difference. So what we are doing is you are removing the effect of surface contaminants, because surface contaminants affects the work function value significantly because it's a surface measurement. Also the illumination, many times the atomic force microscope has its own laser. So when I was doing dark and light measurement, your dark measurement is actually not dark because it's already exposed to the laser light of the AFM. So that also gets cancelled out because you are taking two measurements and then you take a difference between them. So it has application in solar cell, resistive memory devices, and thermoelectric material, which I've shown. And presently, we are in fact very much interested in using this technique to investigate semiconductor electrolyte interfaces. That means interface of materials with liquids. So we have now a Kelvin force microscopy. We can do liquid measurements when the sample is under liquid. So this has application in photoelectrochemical devices and also in battery application, because there the electrode is always in contact with the electrolyte. So this is what is the future direction of this work. And before I stop my presentation, I would like to mention that we have this is another aspect of my interest today, that we have established a no-profit company similar to a trust, and which is called Vedyam, 1T Education and Empowerment Trust. And what we are doing is we are developing experiments to teach different concepts to school students, primary and pre-secondary students. And what is shown here is this experiment designed to tell them how the touch screen works, for example. Okay, so it's very interesting experiment. So this is being done for making one make and learn lab for one school in Bhopal. So I'm very happy to share this with you. And all the work which we have done, I think is done by these, their students are the workforce. So 40 PhD students, they have done this work. And also these collaborators, Professor Fang, Cruz, and Professor Bruger from Germany, where we had strong collaboration on 2D materials. They have contributed, so I acknowledge. Thank you very much. So I will be very happy to participate in discussion with. Yes, thank you very much.
Thank you very much. Thank you very much, Mehta, Professor Mehta. We have many questions, but this lecture was fascinating and interesting. And you used Kelvin force microscopy in a fantastic way to work on it. We just learned about it, but you enlightened us about its applications in these two important areas nowadays: solar cell, and then this is thermoelectric material, which is like environment saving techniques. So this is the first question comes from the Sandeep Day, that how to identify p-n homojunction by Kelvin force microscopy. Hello.
Hello. Yes.
Yes. So first question is from Sandeep Day, how to identify p-n homojunctions by Kelvin force microscopy.
Okay. So I think there should not be any difficulty. I don't, because the junction which I showed you, bismuth telluride and molysulfide, in fact that is a NN junction. Okay, junction between two anti-materials, and antimoney telluride and molysulfide is a PN junction. So I don't see any difficulty in the same technique which I showed you can be utilized to investigate that homojunction. If the person who is asking the question, he can tell me what is the difficulty he is thinking, but in my views, there should not be any difficulty. The technique which we described can be utilized.
Sir, probably his question is how to identify the PN junction, PN homojunction.
No, because when we will do this is he asking how to identify P side and N side, or how junction?
P
Because
and
junction
homojunction. P and N homojunction.
homojunction. Yes. So when you do this surface mode and junction mode and take the difference, you will know, you will get the information about any junction which is present on the top surface and your base material.
The second question.
No difference, no difficulty. The way we have explained, same way, even that homojunction can be done.
I hope
Identified, you are asking which homojunction is?
PN junction.
yes.
PN.
PN. So that's what we have shown. All these junctions are PN junctions only. So what is identification? If you're saying you have to identify which material the junction is formed, what this technique will give you is the work function value. Okay, it is giving you the work function value, and once you know what is the work function of your silicon or the other material which you are utilizing, you can find out, you can identify what material this junction is made of, because you know the work function.
I hope his question was answered. The second question is from our student, BTech student, the Chinmay Shukla. Yes, sir, is there any role of N-type silicon thickness in measuring the voltage when at the back contact point for junction voltage measurement?
Can you repeat it, please?
Hello.
Repeat the question, please.
Is there any role of N-type silicon thickness in the measuring the voltage when at the back contact point for junction voltage measurement?
Okay, so this is a good question. I think what the student is asking is that when we are doing these junctions, so what is the role of, or what is the role of this N-type silicon and the back contact?
Yes,
is a good question. So what I would like to answer is that what we are doing here is, when you do the surface measurement, then what is important is the junction between the tip and the top surface. That's only important. But when you're doing this measurement, in this case, what is important is back contact. And then the junction between the back contact and silicon is also important. That's what the student is asking, I think. What is the role of the back contact and N-type silicon junction? And then the second junction, because there are two junctions here, back contact, N-type silicon. Then N-type silicon and graphene. The junction between graphene and N-type silicon is what we want to investigate. But this junction between the back contact and N-type silicon is also coming into the picture. But what we are assuming is that this is a ohmic contact. The back contact is an ohmic contact, and so there is no voltage developed there. So there is no voltage here. The resistance, electrical resistance is less for the back contact, and it's an ohmic contact. So the voltage which is present at the back contact and N-type silicon is negligible in comparison to the voltage which is present in the junction under investigation. So that voltage, that contact can be neglected. If this contact is not ohmic and its contact resistance is not under control, then of course it will interfere in the measurements. So you have to ensure your back contact has a very small resistance and it is a ohmic contact. Okay?
Yes.
Thank you.
Okay. One more question is from Rupam Mandal. What is the wavelength of light used during the KPFM of graphene? Can KPFM map the band bending at GS-SI interface?
Yeah. So the KPFM measurement, because we did dark measurement and light measurements. Yes. Okay. So yes, I think what the question is, what is the wavelength of this light? This is a white light. This is a white light source at AM 1.0. AM1, because this is a solar cell. So we used air mass AM 1.0 using optical fiber, and it falls on the solar. So it is a white light. It is comprising of all the wavelengths which are present in white light.
He has one more question. Can KPFM map the band bending at the graphene silicon surface?
Exactly. What you are measuring is, you are making that measurement only. What is the voltage which you are measuring? That voltage is corresponding to the junction which is formed, or the band bending, or which is formed at the junction, at the top surface between the graphene and silicon. That is what is being measured. So answer is yes, you can do that measurement.
So his question is, can this CAFM can be performed on metal, semiconductor, metal-like sandwich surfaces?
Yes, yes. Conducting atomic force microscopy gives you the conductivity. And as I showed you, it gives you the conductivity of the top surface. You can see that, what I showed you earlier.
Yes, yes.
Okay, so conductivity of the top surface is what you get. So if you have a junction or something, but the conductivity which you are measuring is of the top surface. That's important, because that it is a spreading resistance, and there you make the top 15 to 20 nanometer layer. That is where is contributing to the conductivity. The conductivity of the other part is, you are not making, it's not coming into the picture. Okay, so this red dot which you are seeing here, that is being investigated in conducting atomic force microscopy, even if your thickness of your sample is very large. Only the top surface, top few nanometer, 15 to 20 nanometer are under investigation. 2 to 3 times the tip area. The depth is 2 to 3 times the tip area.
Okay. So another question which is similar, that can CAFM distinguish between interface and bulk contribution in the conductivity? Hello.
It will give, conducting atomic force microscope will give you surface conductivity. Surface conductivity. You are getting information about surface, not the conductivity of this region, not the bulk conductivity. In fact, bulk conductivity you can measure with many other techniques. You in fact require a technique to measure surface conductivity, and that's why you have a surface conducting atomic force microscope. So you make measurements using conducting atomic force microscope, and then make measurements using normal electrical contact. That gives you bulk conductivity. You can compare with the surface conductivity variation using CAFM. CAFM is for making surface measurement and from point to point. From point to point. So you are generating a map of surface conductivity. Bulk conductivity can be made, measurements can be made by other techniques and compared. And the results can be compared.
So really very fascinating lecture, Professor Mehta. And it is as usual, we are fascinated to hear your lecture time to time. And you have shown that the interface, study of interface can give how much in-depth information about the device property. And that's what basically any electrical or the nanotechnology student is looking for. They must focus on the interface. The moment they are making a junctions, the interface play a major role. So we are really thankful to you for the very, very fascinating lectures. Although we want to take for some more questions, but due to the time constraint, I will provide the email ID of yours, or we'll take the question and forward to you for the response. So thank you very much for your time and your kind presence to our workshop. Thank you very much, sir.
Thank you very much. It's always interesting and useful to interact with your students, which I have given many lectures. So I will be very happy to answer their questions by email. Thank you very much.
Yeah, Pooja.
The next speaker, Dr. Ramjani Chaudhary, can be made the co-host for sharing this screen.
Thank you very much.
Thank you so much, sir.
Very much. So,
Thank you, sir. Our next talk will be by Dr. Ramjani Chaudhary. Dr. Ramjani Chaudhary is presently working as Scientist G in UGC DAE Consortium for Scientific Research Indore. He has done his PhD from University of Pune in joint collaboration with University of Maryland, College Park, USA, and Inter-University Accelerator Center, New Delhi, India. He is a recipient of DAE Young Scientist Award His research interest deals with structural electrical magnetotransport and resonant photoemission studies of magnetic oxides, thin films, and heterostructures. He has guided a number of PhD students and have many publications in international peer-reviewed and index journals. He will share his research work on material characterization using index sources. I will welcome you on this virtual platform, sir. Sir, you have 45 minutes followed by 10 minutes of question and answer session. I request you to please conclude the work in this timeline. Thank you. Over to you, sir.
Thank you, ma'am. I will share my screen.
Welcome, Ramjanay ji.
Namaskar, sir. Welcome. Unfortunately, I'm not able to see myself. Am I visible?
We are able to see your screen.
Okay, fantastic. Great.
You can just go to the presentation mode. That's all.
Fine. Yeah, absolutely fine.
Yeah.
So, okay, good morning and namaskar to all of you present here. And I just wish that you all are fit, fine, healthy, and in good spirit with your near and dear ones, with your neighbor ones, and of course, all of you in this pandemic situation. Before I start my presentation, I must be thankful to organizer members, in particular Dr. O.P. Sinha and Dr. Richa, for giving me this opportunity to share some of our interests in or experience when we are using this industry proton sources. So, I mean, I'm from UGC DI Consortium for Scientific Research, and you can see that in this Indian map, our consortium is actually located at 4 different places. Indore is the main center. We have another center in Mumbai and one in Kolkata, and a node in Kalpakkam. And the mandate of our consortium is to promote, encourage, and support the research using mega facilities which are created by Department of Atomic Energy at these places. And you may know that in Mumbai we have BARC, in Indore we have RR-CAT synchrotron source. In Kolkata we have variable electron cyclotron center. And then Kalpakkam we have low energy accelerator. So at all these places we provide access to these facilities to university researchers. And this is one of our main mandate. And in that concept, we have several other in-house research facilities also for different characterization techniques, like magnetization measurements, thin films deposition, spectroscopic techniques. Then we have X-ray diffractometers. We have several microscopy techniques. We have transport and thermal measurements. So you all are encouraged to use these facilities, and I'm sure many of you are already using these facilities. And you may not have to worry about any other thing. You, of course, the time slot becomes crucial depending on the how much demand that particular facility is in. But we try to accommodate many of, I mean, almost all the users whoever approach us for these measurements. Of course, these are completely free of charges, so you do not have to worry. We will take care of your logistics, travel support, and local accommodation. So do not worry about those aspects. You just worry about your problem in physics. So coming to our own group, I mean, I'm from thin film magnetization group, and we have generally this, we use this pulse laser deposition, which is attached with reed, where we have this oscillations. From that reed oscillations, we can know the number of layers which are grown. We can also probe the epitaxial nature of the films. Then we have photoelectron spectroscopy measurements, which provide us the information related to the valence band spectroscopy or the core level spectroscopy. So that is below the Fermi level. And then we have this X-ray absorption spectroscopy, which is recently upgraded to perform X-ray magnetic circular dichroism experiments. There one can also probe the unoccupied states. So unoccupied states are those states which are beyond Fermi level. So by combining these valence band spectroscopy and this X-ray absorption spectroscopy, one can get an idea of the complete electronic structure across the Fermi level. And then, of course, we have split VSM also to probe the magnetic property of those thin films, which are generally true. Coming to the plan of my talk, I'll briefly talk about this indus synchrotron source, then spectroscopy techniques, which will include this X-ray photoelectron spectroscopy, valence band spectroscopy, then resonant photoemission, and then X-ray absorption. And I will pick up one such example on iron doped TiO2 thin film, which is a dilute magnetic semiconductors, where I will show the utility of these different facilities or characterization techniques in order to probe certain physical concepts or mechanisms behind a particular phenomena, which is giving rise to unusual properties in these thin films, followed by conclusion. So this is related to Indus 1 synchrotron source. I will not talk in detail about Indus sources because my colleague from DARC, Dr. Shilpa Tripathi, who is the next speaker, she will be talking in detail about these things. So I leave this platform for her. I'll just briefly talk that at Indus 1 we have different beamline facilities, and UGC DACSR has constructed this particular beamline, which is angle integrated photoelectron spectroscopy beamline with the energy source from 10 electron volt to 200 electron volt. And I'll be talking results obtained from this particular beamline. Then again at Indus 2, we have several beamlines working, and our consortium is involved in this soft X-ray absorption spectroscopy beamline, which is recently upgraded to also performing for this X-ray magnetic circular dichroism with the energy range 100 to 1200 electron volts. So that energy range actually covers many of the elements like nitrogen, oxygen, or transition metal elements and things of that nature. So one can probe various interesting properties using this particular beamline. Now coming to this photoelectron spectroscopy, we know that what is photoelectron spectroscopy? It basically works on photoelectric effect, the Einstein's photoelectric effect. You shine a photon on a metallic surface, and what you see that there is an ejection of electron. But that is not completely confined to the metallic surface only. It can be true for any element or for any material, right? So what it has to do to knock out an electron, I mean, we know that any element has certain electronic structure, and when we talk of its electronic structure, then it has electrons in say 1s level, then 2s, 2p, 3s, 3p, 3d, etc., right? And at all these energy levels, the electron's binding energy is rather fixed. Okay, so if I shine a photon whose energy is higher than the binding energy of that particular electron in that particular core level, so what it will do, that electron will absorb that photon, and with that excess energy, it will come out of the material by overcoming that work function, and that extra energy is converted into the kinetic energy, right? So if I can measure the kinetic energy of the ejected electron, we can actually know that what was its original binding energy, because we know the kinetic energy, we know the incident photon energy, and from their difference, and of course the work function also comes into picture, and in this particular thing, the spectrometer work function is always constant, so we know that parameter also. So from there we know that what is the binding energy of the electron which is coming out. Now you can understand that if I'm just taking a simple example of zinc oxide, then zinc has also 1s electron and oxygen has also 1s electron. But the binding energy of that 1s electron for zinc will be different than binding energy of 1s electron for oxygen, right? So that is where it can allow us to understand, just by measuring the kinetic energy, since we can estimate the binding energy, we can know that what element is present in that particular material, number one. Number two, at what energy level that electron has actually come out, because the binding energy of these ejected photoelectron, this is their characteristic, this is their, that is how they are known. Okay, so one thing which is very important here is that it is a highly surface sensitive technique, and this also one has to look into the fact that since in this any material there are electrons in the core levels, there are electrons in the valence band. So to eject an electron from the core level, since their binding energy is very, very high, therefore to eject that particular electron, you will require a higher energy. and that is where the X-rays are generally used. Okay, so that particular technique is called as X-ray photoelectron spectroscopy. And to eject an electron from this valence band, you require a rather lower energy because they are just at the valence band. So their energy difference with respect to Fermi level is rather low. That comes from say 10 electron volt to 50, 60 electron volt. And for that, even ultraviolet light is also sufficient to eject that particular electron. And that we call as ultraviolet photoemission spectroscopy. So we have two techniques. One is X-ray photoelectron spectroscopy, where we talk about the core electrons properties, and we talk about the valence band spectroscopy or ultraviolet photoelectron spectroscopy. There we talk mostly about the valence electrons. And here I'm just showing you some of the examples that how does this spectra actually look like. So if I just shine say some 1486 electron volt of photon on any material, which is say lanthanum, strontium, manganese, oxygen. So you can see that from all these elements, the electrons are coming out, and therefore you have those peaks appearing, right? So this is called as survey spectra. And then you can just focus on this particular element in a narrow range scan. And from there binding energy positions, you can get an idea that what is the ionic state of that particular element in that particular material. Okay, so these are the core level spectra, and here you can see, and you can also notice that the binding energy in all these spectra are in few hundreds of electron volt. Whereas if you look at these spectra, which is shown below, the binding energy is only 0 to 8 electron volt or 10 electron volt. So from there, you can get an idea that this is nothing but the valence band spectroscopy. Number two, you can also notice that how will this give information? What new information will it give you? So you can know that the difference between a metallic system and an insulating system is that in a metallic system, your Fermi level is between this valence band and conduction band. So they are kind of overlapped. So you will have a finite density of state at the Fermi level. But in insulating layer, there is nothing like that. There is a gap between this valence band and conduction band. So from here, you can see that at this Fermi level, which is 0 electron volt, you have a rather flat band. That means there is no density of a state. But when you lower down the temperature, then you see that there is a finite density of a state. So what does it indicate? It indicates that at higher temperature, this particular material was insulating in nature, whereas at lower temperature, it has turned into the metallic character. Okay. So how do we do those experiments? To do those experiments, we need certain sources because we need photons to eject those photoelectrons. So, of course, the name suggests that for using X-ray photoelectron spectroscopy to eject the core electron from the core levels, we need higher energy. So, therefore, X-rays are used. Okay. So, we have magnesium K alpha as well as aluminum K alpha. Whereas to eject an electron from this valence band, we have this ultraviolet photoelectron spectroscopy. And, of course, we also have this synchrotron radiation. This synchrotron radiation can also cover all this energy range from ultraviolet photoemission to X-ray photoelectron spectroscopy. And it gives us better resolution in terms of experiments. And these are the specifications of our angle integrated photoelectron spectroscopy beamline, which is situated in the Swan synchrotron source at RRCat. And we can vary the temperature from 450 degrees centigrade to liquid nitrogen temperature. So we have lab sources like aluminum K alpha and magnesium K alpha also, as well as it is connected with the synchrotron beam where we cover the energy range of 10 to 200 electron volts. So that means we can cover the ultraviolet photoemission spectroscopy part also. So how does it provide information in what different way? This is something which we should understand. So as I said earlier, that XPS is element specific because the binding energy of different elements are different, therefore they become characteristic. So just by looking at the binding energy, we can understand that what element is present in that material. Also, for different ionic states, say for instance, I am talking about iron oxide. We know that iron oxide can exist in many phases. It can exist in FeO phase, it can exist in Fe3O4 phase, it can exist in Fe2O3 phase. So in all these different oxide phases of iron, what is different is the ionic state. So Fe2 plus will have a different binding energy than the Fe3 plus. Of course, Fe3 plus will have a higher binding energy than the Fe2 plus. So just by looking at their binding energy position, we can know that what kind of ionic state it is present. And of course, if your system, in your system only iron is present, then again its binding energy will be different. So it gives us the information about the kind of element which is present. It also gives us information about the kind of ionic state in which that particular element is present. Okay. Now, coming to this valence band spectroscopy. As I said earlier, that this valence band spectroscopy gives information about the valence electrons, and those valence electrons are nothing but, I mean, if I just talk of say zinc oxide, then you may know that zinc outermost electron is 4s and oxygen outermost electron is 2p. So both of them hybridize to form this zinc oxide structure. So you do not know actually that in that valence band, where is zinc 4s electron or where is oxygen 2p electron. Since they are hybridized, so their binding energies may be very close to each other, and therefore the different features which we generally observe in valence band spectroscopy cannot be attributed to particular element, because those features are so close that they lose their identity, that what was their original binding energy in terms of valence band electrons, right? So what it gives information is that it gives information about the molecular orbital in which that hybridization is actually forming, and also this binding energy of individual zinc or oxygen, or the outermost zinc electron and oxygen electron, they are hugely affected when they form zinc oxide because of the proximity, because of the overlap, because of the hybridization that they go through. So it is not very obvious to understand that a particular feature in valence band spectroscopy arises because of what, whether it is arising because of the zinc valence electron or it is arising because of the oxygen valence electron. So to probe those particular features, resonant photoemission spectroscopy is something which will provide information related to that. And here I'm just giving you example of what I'm trying to convey. Here, for instance, if I'm having TiO2, so this is titanium core level X-ray spectroscopy, and you can see that from their binding energy positions, I know that titanium is present in this system in 4+ state. Similarly, for this iron, since this shows maxima close to 709 electron volt, I know that iron is present in 2+ state or 3+ state, because iron metallic has a binding energy close to 706 electron volt, and which is not there, right? So from there we know that, okay, those are the attributions to those particular ions in that material. But if you look at this valence band spectroscopy, so you see that this is a valence band spectroscopy just by looking at the binding energy, since they are very low. So you have this feature, you have this feature. Now you do not know whether this feature arises because of iron or oxygen. This is the valence band spectra of iron oxide, right? So similarly, this is LaSrMnO3. So we have again different features. We do not know that what is the origin of these different features. Similarly, in this iron doped titanium oxide, we have this feature, we have this feature, but we cannot confirmly say that why this binding energy feature, whether it is arising because of iron or it is because of titanium or it is because of oxygen. So to probe those particular things, resonant photoemission spectroscopy comes into picture. Okay. Now, what is resonant photoemission spectroscopy? I'll just briefly talk about that. See, in a normal photoemission process, just imagine that your transition metal element is having electronic configuration like say 3p6 3dn. Okay. So in a normal photoemission, you shine a photon. So you have this p6dn original electronic configuration. You shine a photon h nu. So what it does, it knocks out an electron from d level, and you have this configuration p6dn minus 1, and then this ejected photoelectron, right? So this is a normal photoemission process. Now we know that there is an energy gap between this 3p level and 3d level. If I tune my incident photon energy in such a way that it is exactly equal to the energy gap between 3p to 3d level, so that this h nu is exactly equal to the energy difference between this 3p to 3d level, what it will do? It will allow that p electron also to excite into d electron, right? Because this energy level allows that that photon energy absorption by 3p electron, so that it will go to 3d electron. But then that becomes energetically unstable because you have a hole in the lower energy state and you have more electrons in the higher energy state. So to overcome that unstable state, again that excited electron comes back to the ground state. But before coming back to that ground state, it transfers that so-called emitted photon energy to knock out an electron which is already present in that 3D level. So that electron is emitted. So in a way, what I'm trying to say is the following. We have P6DN and then you shine a photon. So what this photon did, since this photon energy is exactly equal to the energy difference between 3p to 3d, so it knocked out an electron from this 3p to 3d. So you have this configuration like 3p5, 3d, and plus 1. Now that becomes energetically unstable. So this excess electron again comes back to p. So you have this p6. But before coming back to this p level, that extra energy is used to knock out an electron from already existing d level to the vacuum. So you have again a p6dn minus 1 state plus photoelectron. So what does that mean? That means that at that particular photon energy, when that photon energy is equal to the energy difference between 3p to 3d level, you allowed another channel for photo emission to take place. So that means you have now two channels open for photo emission. One is normal photo emission and one is this resonant photo emission. And that allows the enhancement in the intensity at that particular photon energy. Now remember, different transition metal elements will have a different energy gap between 3p to 3d level. Therefore, it is also a characteristic to probe that what kind of transition metal element is contributing to that particular valence band feature. So that is the utility. But to probe this experiment, what we need to have? We need to have tunability of incident photon energy. Only then we can vary incident photon energy. See, your material doesn't, you do not have an idea that what kind of element is present or what ionic state is present in your material, right? To probe that, to allow that resonance to take place, you have to gradually change the incident photon energy up to the extent that it allows that resonance phenomena to take place. Therefore, you need a tunability of photon energy, and that is where synchrotron source comes into picture. And here I'm giving you one example of how this resonant photo emission allows us to understand. See, this is some cerium oxide film. Okay. Now, in this cerium oxide, if I vary this incident photon energy, say from 118 electron volt to 127 electron volt. So you can see that 118 electron volt is this black color. Then if I further increase the incident photon energy 121, the intensity of this particular feature increases. Then at 122, it further increases. Then 124, again, it starts coming down. So that means this particular feature shows a maximum intensity at 122 electron volt. And it so happens that cerium in 3+ state will have an electronic configuration 4d10 4f1, right? And at that particular 122 electron volt, the gap between 4d to 4f is completely matching, and therefore it allows that resonance phenomena to take place. So from there, we know that this particular feature is arising because of the cerium 3+ in cerium oxide, CeO2. Of course, you can always wonder that in CeO2, we should expect that cerium should be present in 4+ state, but here it is only 3+. But that is arising because of the oxygen vacancy, and that is where this cerium oxide is used as a fuel cell. Now you look at this particular feature. This particular feature shows maxima close to 125. Now it is no more 122. So that means this 125 is nothing but cerium 4+. So the actual cerium 4+ in CeO2 appears at higher binding energy position, and the near Fermi level position feature is attributed to the cerium 3+. So that means, excuse me, that means oxygen vacancy induced defect has created a state very near to the Fermi level between this cerium oxide conduction band and valence band. So this is how this cerium oxide is beautiful in understanding the utility of resonant photo emission in this particular composition. Now I pick up this test example of iron doped TiO2 in this system. We know that this is a very popular dilute magnetic semiconductor. So what is that? We dope magnetic impurity in an otherwise non-magnetic semiconductor with an intention that the original semiconducting material, which was non-magnetic, should turn into magnetism, but not at the cost of forming clusters of those doped transition metal element. Because if you dope those transition metal element, the cluster itself will show you the magnetic property, but not the whole material uniformly, right? Of course, the purpose of having this dilute magnetic semiconductor is to tune or to couple the electrical property with the magnetic property. So if you apply magnetic field, the electrical property should change, and if you change electric field, the magnetic property should change. That is the whole purpose, the coupling between the electrical and magnetic property. So in your system, if you are having a cluster, then cluster will give you a different magnetic property, and it has nothing to do with the overall electrical property of the material. So what is the desire? The desire is that the induced magnetization in this system should be mediated by the charge carrier and should not arise in an isolation. Okay, so that is the importance of this particular material. And for this particular study, we picked up this titanium oxide because of its very cerebral properties, and we know that this TiO2 arises or exists in various phases, NRTS, rutile, and brookite, and it is very important to establish a single phase of any of this TiO2, and that is why it is very important to optimize a proper condition to one of these phases. Okay, so what we have picked up is to dope iron in this TiO2. We know that TiO2 is a wide band gap semiconductor with a band gap of say 3.4 electron volt. So with that 3.4 electron volt, we should expect that it should be a transparent insulator, right? And we dope iron in the system with an intention that it should induce magnetization. So when we dope iron, then there can be certain issues. And what are those issues? Whether the iron is forming a cluster, number one. Number two, whether iron is forming altogether a different compound. Number three, even if there is induced magnetization in this system, whether it is in carrier mediated or not. So these are some of the things which are very crucial to probe about the intrinsicness of this particular metal, and these are the experimental conditions which we have used. And okay, I'm just giving you here is the phase diagram. We varied the iron concentration from 0 to 4%, and we varied the oxygen partial pressure also. So what we see that we have pure NRTS phase only when we deposit films at say 10 millitorr of oxygen partial pressure, and these films were grown on lanthanum aluminate. And you can see that it shows a very good epitaxial properties. What is epitaxy? When your film retains similar crystalline arrangement as that of the substrate, then we call that film as the epitaxial film. Now you have chosen your substrate like a single crystal, and your film is also behaving like a single crystal. So therefore, that is the utility of epitaxial film. Please remember, epitaxy is not the property of the film. Epitaxy is a relation between the film and the substrate. Number one. Number two, here is the X-ray diffraction, and you may show that you are seeing this broad peak and all that. You will say that, okay, if your film is like a single crystal, why these peaks are broad? Remember, these plots are shown in the log scale. Why is it important in thin films to plot X-ray diffraction in log scale? Is because your substrate is having intensity of say few hundreds of thousand, and your film is having intensity of say around 1000 count or few hundreds of count. So in the background, in the linear background of say few hundreds or few lakhs, 100 or few thousand may not be easily visible. But the moment you plot them on log scale, few hundreds become a few lakhs become some 5 or 10, and thousands become 3 or 4, right? Rather between 2 and 3. Therefore, you can easily probe. So it is very important, if you do not want to hide your impurity, to plot your thin films X-ray diffraction on log scale. Okay, now coming back to the actual happenings at the elemental level. So I doped the iron in the system, and what we see that iron is showing this particular feature, and it doesn't show any feature close to 706, which should have occurred for if iron was present in the metallic cluster. If iron is forming its own cluster, if it is forming its own group, then the kind of bonding that is existing between iron will be like a metal, and therefore its valence state should be like a 0, which is not the case. But what we see is that we have a fair good peak at close to 709, which could be fitted with 2 peaks, suggesting that in particular system, iron is present in 2+ and 3+ system. Okay, what about titanium? Titanium in TiO2, we should expect that titanium should be in 4+ state. But what do we see? That titanium is present in titanium 3+ and 4+ state. What could be the origin for this titanium 3+? The origin of this titanium 3+ is nothing but the oxygen vacancy. I will briefly talk about that. Now, before talking about that, let me just show you that how this valence band spectra look like. I just showed you the core level spectra. Now coming to the valence band spectroscopy, because if you dope iron in the system, what will be the most affected thing? The most affected thing will be the valence band electrons, because core level are deep inside. They are very influenced by the nucleus. They do not bother much about what is happening in the outside world. They are not much affected. But the valence band electrons, they are the mostly affected electrons with any small perturbation that is taking in its vicinity, right? So if you look at this valence band spectra, the blue one shows the valence band spectra related to this TiO2, and what you can see that close to Fermi level, which is 0, you do not have a flat line. So that means there is a finite density of a state. So what does that mean? The system should show a metallic behavior, number one. Number two, in iron doped TiO2, what do we see? That beside this particular feature, we have a new feature B also, which is appearing. Okay, now that origin we may have to understand that what could be the origin of this feature A as well as this feature B. Okay, so now a few questions are here. What is the origin of this finite density of a state? What is the origin of titanium 3+ as observed in X-ray photoelectron spectroscopy? So please remember, as I said, that these are in thin film forms, and in thin films, the oxygen vacancy formation is quite natural. So when we have this oxygen vacancy, then the unattended 2 free electrons are available there. Those 2 free electrons can do a few things. Either both of them go to their neighboring titanium site and convert them into titanium 3+, or both of them can be delocalized, and if they become delocalized, then you will have a sufficient free electrons in your system. Or another possibility could be that some of the free electron will go to the neighboring titanium 4+, and some of them will be delocalized. So in that way, you will have some delocalized electron and you will have some titanium 3+ also. In the XPS, we had the indication of titanium 3+. So that means those free electrons are converting titanium 4+ into titanium 3+. The finite density of a state at Fermi level indicates that we have some density of states at Fermi level also. That means we are having some delocalized electron also. So if there are delocalized electron, then the system should behave like a metallic behavior. And please look at this particular resistivity behavior. What it shows that at room temperature, the temperature coefficient of resistance is positive. It is not like a semiconductor. It is showing like a degenerate semiconductor where you have a finite density of a state at the Fermi level. So that means in this particular system, we have some oxygen vacancies, and that oxygen vacancy is usually affecting the electrical property. Of course, in TiO2 with the band gap of 3.4 electron volt, you will never expect it to behave like a metallic or degenerate semiconductor, right? Or even a finite density of a state at the Fermi level. So all these observations indicate that in this system, we have this oxygen vacancy, and those vacancies are forming a kind of defect state, or rather shallow donor level just below the Fermi level, which can be attributed to this feature A. But why you should expect this? Why you should believe me that, okay, this feature A is because of this oxygen vacancy induced defect state, which is titanium 3+. To confirm that, we performed resonant photoemission. How do we do that? We record this valence band spectra and vary the incident photon energy, say from 40 to 62 electron volt. Okay. Why do we vary this incident photon energy range? Because we know that titanium 3+ has a gap of 3p to 3d has a gap of 46 electron volt, and iron has a gap of 56 electron volt. So if feature A or B is arising because of either iron or say titanium, we should be able to observe this. And then you can see that how these individual features intensity is actually varying in this particular system. To really monitor this very closely, what we should do, we should plot their intensity separately with respect to incident photon energy. And what do we see? That feature A shows maximum close to 46 electron volt. So that means the feature A was nothing but because of this titanium 3+, because for titanium 3+, the gap between 3p to 3d is at 46 electron volt. But for iron 3p to 3d, the gap is 56 electron volt. And you can see that this feature B was showing this gap, resonant maximum intensity at 56. So that means feature B came because of this iron doping in the system. Another important thing is that feature B also shows some intensity at 46 electron volt, which was titanium 3+. What does that mean? That means the feature B, which was iron derived state, was nothing but the hybridized state of iron and titanium 3+ in the system. So in a way, the doping has caused oxygen vacancy, and oxygen vacancy induced defect state is actually hybridizing with the magnetic impurity in the system. So this is very important. And if you just subtract or separate out the titanium contribution and iron contribution in the valence band spectra, how do we do that? Now from resonant spectra, we know that at 46, the maximum contribution is because of titanium 3+, and at 56, maximum contribution is because of iron derived state. So if I just subtract this valence band spectra recorded at 56 with some non-resonant state, then we should see this iron contribution. So what do we see? That iron contribution is also available at Fermi level, which is 0, right? So that means the magnetic impurity is interacting with our charge carrier. So this is another confirmation that in the doped magnetic impurity is not only is not present in cluster form and also interacting with the charge carrier in the system. Now, what about the magnetization in the system? Please remember that this iron dope system, as expected, that iron doping, of course, we know that iron is a good magnetic impurity and it shows a very good magnetic hysteresis. Surprisingly, undoped TiO2 also showed magnetic hysteresis. What was the origin? The titanium 3+, oxygen vacancy induced defect state. Titanium 3+ has a vacancy, has a local magnetic moment of 1 μb, because 3d1, you have one unattended electron, right? So that one attended electron gave rise to local magnetic moment, and they are kind of exchange interacting with each other, and that causes this induction of magnetization in undoped TiO2 also. And here is the high temperature magnetization, which showed that these films have Curie temperature way beyond room temperature. Okay. Now, how do I confirm that, okay, magnetic impurity is only present at the titanium site only? So as I said that we have recently upgraded our XCS system with this XMCT experiment, and XMCT experiment is a tool which will allow you to probe element specific magnetic moment, number one. Number two, it will also give you information about the spin contribution as well as orbital contribution to the magnetic moment. And here it is shown, and from this spectra we can confirmly say that the origin of magnetization in this system arises at the iron level, which is also substantiated with the induction of oxygen vacancy in the system. And these are some fingerprints of how Fe3O4 XMCT looks like. I'm not going into detail about those things. Now coming to resistivity behavior. Now so far what we have established is that the doped magnetic impurity is not in cluster form. They are kind of substituting. The charge carriers are also interacting with the magnetic impurity, as is reflected from this resonant photoemission spectroscopy data. The system shows degenerate semiconducting behavior. Now, whether this interaction of charge carrier with the magnetic impurity, does it give some magnetoresistance in the system, and what is the origin of this low temperature semiconducting like behavior? So there are several explanations to that, but as I said earlier that we have titanium 3+ in the system, which is acting like a local magnetic moment, and that local magnetic moment, when those charge carriers come in the vicinity of that local magnetic moment, then it scatters those charge carriers, and that gives rise to some scattering phenomena, and its dependence is given by log T. And the system shows very good Kondo behavior. So that means there is kind of antiferromagnetic interaction between the impurity spin, which is by this titanium 3+, and the conduction electron in the system, which weakens the magnetic interaction. So in a way, there are kind of two competing interactions in the system. One is like RKKY like interaction, which is inducing magnetization in this iron doped TiO2 or undoped TiO2, whereas some local magnetic moment interaction, which is antiferromagnetic with the charge carrier, that gives rise to condo interaction and it weakens the overall magnetic interaction. And here is the magnetoresistance. You can see that this magnetoresistance, the system shows around 1% of magnetoresistance, but more than that, what it is showing here is that the charge carriers are indeed interacting with the local magnetic impurity in the system. Okay, now what I said is that in undoped TiO2, the origin of magnetization was the presence of charge carrier as well as the presence of local magnetic moment in terms of titanium 3+. And those charge carriers are actually mediating the magnetic interaction between the magnetic impurity of iron in this iron doped TiO2. What is the origin of charge carrier? The origin of charge carrier was nothing but the oxygen vacancy in the system. The oxygen vacancy gave rise to 2 unattended electrons, and those unattended electrons could be delocalized in the systems, and some of them converting titanium 4+ into titanium 3+. So if I kill that unattended electrons or the delocalized electrons, how do I kill that? So if I kill those unattended electrons, then there are no charge carriers available for magnetic interaction. So how do I kill that? We anneal those films in the presence of oxygen. And if I anneal those films in the presence of oxygen, what do we see? That the magnetization has drastically dropped. That means the oxygen vacancies are annealed out. Now there are no more charge carriers available for magnetic interaction or to induce the interaction between the magnetic impurities. Therefore, the magnetization has considerably come down. Now, how do I really further confirm? You can
sorry
see,
for disturbing, sir, sorry for disturbing. We will be grateful if you can conclude your talk in 5 minutes.
Sir, I will take 1 more minute. That's it. I'm almost done. Yeah, this is my very last slide. Yeah, thank you.
Thank you, sir.
Okay, sir, welcome. So you can see that if I just anneal my system in the presence of oxygen vacancy, you can see that this high temperature degenerate semiconducting like behavior, which was giving this metallic like behavior, completely turns into the semiconducting, and you can see a sharp increase in the resistivity. So all these conclusions, what does it confirm? That the electronic structure of TiO2 is hugely affected by the iron doping in the system. Number one. Number two, the system behaves like a degenerate semiconductor. Number three, the charge carriers are interacting with the magnetic impurity. And of course, such a study will give us an understanding about the evolution of electronic structure and its correlation with the magnetic properties in the system. Okay, and I will just acknowledge some of my friends who are part of this whole work. This is my group at present. These ones are the current students, the right ones and the bottom ones are done with. And yeah, they all have given enough trouble and they are troubling. And that is continued even today. Thank you very much for your attention. Ready to take up your questions if you may have.
Thank you very much, sir, Chaudhary. Is there any questions from the panel or anyone?
Yes, sir.
Yes.
Good afternoon, Ram sir. Thank you very much for giving us the fundamental and in-depth knowledge of XPS and resonant XPS technique. Sir, it's very good. Your lecture means we have learned a lot of things. Sir, I have 1-2 doubts. This is, sir, regarding the analysis of XPS spectra. Generally, sir, how we can differentiate for this binding energy. Let's say we have a composition of semiconductor nanostructure, and now it is difficult, like people like us, that whether the peak is for, let's say, zinc oxide and iron oxide composite, that this is for the ionic state of zinc oxide or ZnOH whole twice, or ZnO, for example. This is just an example, sir. So how can we confirm that? Or this is same with iron also, sir, Fe+2 state, Fe+3 state, or FeO state. Sir, then how to confirm that? Because using that peaks, it is very difficult to analyze. Most of the time we have to take the reference of some papers. Sir, how to check that?
Sorry, there are so many things mixed up, so I'm a little lost about what you wanted to ask. So please,
Okay.
if I understand your question, in your iron oxide you have FeO or Fe2 plus, you have Fe3 plus.
Yes, sir.
How do I make a separation?
Yes, sir.
How do I identify? Okay.
Yes, sir.
Fe2 plus and Fe3 plus are easy to separate out because there is another feature which is called satellite feature. I didn't talk about that because of the
Okay,
lack
sir.
of timing. The satellite feature of Fe2 plus and satellite feature of Fe3 plus, they appear at distinct positions. Okay, so just by looking at their satellite positions, you can attribute whether in your system iron is present in 2 plus state or 3 plus state. So that is how it can be taken care. Regarding your zinc oxide, so you took example of ZNO as well as this ZNOH twice, if I understand correctly. Is that right?
Yes, sir. Yeah, perfectly right.
Okay, उसमें तो मैं भी नहीं बता पाऊंगा.
Sir, because their peaks are in like
Right. Yeah,
in a very
I
close
understand your
approximation, sir.
Yes. मेरे ख्याल से उस परिस्थिति में आपको तो XRD करना चाहिए.
जी sir, जी
Because
sir. Okay.
ZNOH twice should have a different crystal structure with respect to.
And ZNO has a different crystal
So
structure,
हमने
right,
थोड़ी
sir?
ना कसम खा रखा है कि XPS को ही करना है. There are other techniques
Sir,
also.
एक छोटा सा doubt और है.
Yes, ma'am. Please.
Sir, means sometimes the peaks are very small, humps means the binding energy, and sometimes they are very sharp or broadening one. Sir, is there identify that the binding energy is means the binding is proper or improper, something like that? क्या ये identification उसको भी करता है, sir? If it is a semiconductor structure or a metal semiconductor structure.
What you are asking is that there is some minor.
Sir, minor peaks, small, very small peaks, or sometimes they are very broader ones.
ठीक है.
So means that can relate like that कि sir the binding is proper or something like that. Peak position से like हम कुछ identify कर सकते हैं क्या sir?
Okay.
Means not position, the flattening or the broadening of the peak.
No, broadening of peak, I mean, can be attributed to many things. Like one is your instrumental broadening. Then you have, apart from that, you have contribution from different states. I mean, as I showed that in my titanium, we have contribution from 3 plus and 4 plus. And because of that, we had certain broadening. Otherwise, we could have seen rather a sharp peak, right?
Sharp peak, right.
So similarly, I mean, if you take, say, for instance, oxygen spectra, that oxygen spectra is always like you have oxygen.
Nitish sir, I got a mail from Vandana ma'am.
Yes, ma'am.
Google form भर दिया आप लोगों ने अपने track का.
Sinha sir, can you? Okay, sir, please, Ram sir, please continue.
Yeah. So if we look at the oxygen core level spectra, then what do we see? That we have contribution from lattice oxygen, we have contribution from vacancy, we have contribution from OH radicals, we have contribution from CO radicals. So all those things, since their binding energy positions are very close, therefore they give rise to some kind of broadening. And of course, we may have to be very cautious about what are we going to actually conclude from them. And if we, I mean, then in those cases, that cannot be the only criteria based on which we should conclude something. We should have some other supporting evidence also, because they may not be sufficient, because it has certain limitation.
Okay. Thank you so much, sir. One sincere request, at least once in a year, one class for our PhD students.
Always. I mean, I'll be happy to take that.
Okay, sir.
Sure.
Thank you, sir. I have one question.
Yes, sir.
The problem is that this SPS technique is a surface technique. So problems comes that on the surface, if you measure, most of the time, this is my experience, that you got the higher percentage of oxygen on the surface than in the bulk. It is like copper oxide is there, then you thought that it is a cuprous oxide or copper oxide. So this is a problem in that. How to solve that? This is like you have to go to that profiling or something. How to solve that?
Right. See, uske liye kya hai? I mean, we have certain in situ sputtering source available. So with that sputtering, argon ion sputtering, we try to clean that surface, and you take lead pattern also, and then see that whether you have obtained the original copper oxide or zinc oxide surface structure or not, and then you perform those X-ray photoelectron spectroscopy. Number one. Number two, of course, we do depth profiling also, because in these oxides there are chances that the sputtering rate of oxygen or other elements can be different, and that can affect your stoichiometry, right? So after sputtering, it is very important to re-anneal the sample so that surface is restructured and you get the original structure before you start doing those measurements. So those are the precautions that one should take.
Thank you, sir. This is very, very informative, and then very student. It is everyone. It is a highly informative talk, and we learned a lot about XPS and UPS technique, and use them in various various calculations or various properties of materials. This is highly fascinating. So, any other question from anywhere? So, if no question, then thank you very much.
Sir, yeah, I don't have a question, but I have a sincere request. Can we get a copy of this presentation?
Sure, ma'am. Yeah, sure.
Thank you so much.
I'll send that. No problem.
Thank you.
Thank you, Dr. Chaudhary.
I just have one comment, Ramdani.
Yes,
it's a very nice. Fine. How are you?
Fine, sir. Thank you.
It's a very nice presentation. Excellent work which you are doing.
Thank you, sir.
Just I want to know, have you in this as far as the low energy ion radiation is concerned, do you have any plan to trigger that vacancy and change the states and then have some tunability of ferromagnetic property?
So you are suggesting
using low energy ion radiation?
Sorry, I didn't get your
No,
point.
I'm just asking your comment. What is, I mean, if you change the vacancies and in case of various wide band gap oxide material,
right?
So how far you can tune the ferromagnetic properties?
Well, certainly it is going to change dramatically. I mean, that is quite sure, because see, I mean, as I said, that oxygen vacancy was on a special mission. कि हमको टाइटेनियम 4+ को 3+ में convert करना है, and then I'll allow delocalized electrons to be there, right? So it was on a mission. But in space, I mean, in place of say oxygen vacancy, if I introduce something like say nickel or some other elements, so the acceptability of that foreign element in that host matrix will play a very crucial role in determining its overall electrical, electronic, magnetic or magnetotransport properties. So it will vary from element to element, right? So those, I mean, we have to be very specific that which element I'm talking about. So, but at the end of the day, if it is affecting this oxygen content, the defect concentration or the number of delocalized electrons, it is going to affect all of these phenomena. That is quite certain. Yeah.
Thank you.
Thank you, sir. Thank you for this nice presentation and informative. So thank you very much. And Pooja for next.
Thank you, sir.
Okay.
Our last talk for the morning session is by Dr. Shilpa Tripathi. Dr. Shilpa Tripathi is working as scientific officer in Bhabha Atomic Research Center, Mumbai. She has done her doctoral studies from Devi Ahalya University. She has done her postdoctoral research from Nuclear and Radiation Physics Section, Catholic University Leuven, Belgium, and also UGC DAE Consortium of Scientific Research, Indore, India. Her major research interest includes photoelectron spectroscopy, nanomaterials including magnetic nanoclusters, semiconductor and magnetic thin films and multilayers, and synchrotron radiation and related techniques. She has published many papers in various peer-reviewed international journals and conferences. Today, her talk will be on nanomaterials research using Indus synchrotron radiation facility. I welcome Dr. Shilpa Tripathi on this platform. The platform is all yours, ma'am. You have 25 minutes to deliver your talk, followed by 5 minutes of question and answer session. I humbly request you to please conclude your talk in this timeline. Thank you.
Thank you, Ms. Pooja. Very good afternoon to all of you. I'm very thankful to the organizers for giving me this opportunity to present some of the work I'm performing currently. So I'm just sharing my screen now. Just let me know if you are able to see it. Are you able to see it?
Yes, ma'am.
Okay. So I'm very fortunate that I'm able to work on some of the best experimental facilities available for research and industrial use in India. That is the Indus synchrotron radiation facility. Indus is a unique facility where with a single electron source, we can perform different experiments. We can have various energies like from infrared to X-rays and hard X-rays, UV, visible. We can have many energies, and different experiments can be performed, like we can perform imaging studies on your sample, diffraction, scattering, and even you can make micron and nanometer size structures with lithography technique. That's all available in one hall that is called Indus. Sometimes it happens that we know the some technique, okay, we can use it for a sample is suitable for it, but we don't know what else this technique can give us if we go to a synchrotron source rather than a laboratory source. So I hope I'll be able to show you some of the advantages of this facility here. Each of the topic I'm going to discuss here can be a separate topic of a seminar. So I'll just try to give an overview of synchrotron radiation source, not going into the details. Indus 1 has two sources, Indus 1 and Indus 2. Both of them have a common electron source. We have a microtron where electron energy is boosted to some mega electron volt, 20 mega electron volt, and then it is injected into either Indus 1 or Indus 2. That I will talk about. Then I will give you just a brief introduction of the beam lines we are using, why we call them beam lines, and different experimental techniques that are used there. And then I will discuss some of the important results I'm working on. So, first of all, question arises, if we have a lab source, we have a laboratory Excel source, then why we go to synchrotron source, which is very, very costly, consumes lots of space and money. So why do we need it? First point is we have a very high brightness in the Indus source. Here you can see that a light bulb will give you some brightness. It's very small as compared to synchrotron source. Even the sun is less brighter than these sources. So if you go to synchrotron sources, you can have very high flux concentrated on a very small area of your sample. That means signals will be very large, and you will get a better signal to noise ratio compared to your laboratory based source. That means if you are studying a medicine, for example, even a trace amount of toxic material can be dangerous for human being. So we need to go for a laboratory source for checking that composition. But laboratory source may miss something because it has less flux. But if you are coming to Indus source, then you are giving very bright flux on that sample, so that even very small trace amount of toxic materials can be investigated. So in ppm or in ppb levels, you can investigate with X-ray fluorescence technique. Apart from this brightness, Indus or in general synchrotron sources have many important properties. Like you can have a broad spectral range. Synchrotron is generated when electrons are either accelerated or decelerated. So when they are simply accelerated or decelerated, you just get radiation. But if you are giving them speed of light, just the relativistic speeds, then the spectrum generated has a very broad spectral range. That can be from IR to soft X-rays in Indus 1 and IR to hard X-rays in Indus 2 at the same place. These radiation are very, very focused. They have high degree of collimation, high degree of coherence. They are highly polarized. And one more important property is that it has pulse time structure. It is not a continuous radiation, but you can tune the pulses so that it will appear like a pulse radiation. So you can have one bunch, you can have multiple bunch, or you can have a combination of hybrid bunches. So different kind of experiments can be simultaneously performed with a single radiation source. These are the properties of Indus which makes it very useful for our studies. Uh, Indus 1 and 2, they are radiation sources. Here you can see Indus 1 has a very small storage ring in which we store relativistic electrons with an energy of 450 mega electron volt, and the radiation coming out can give rise to several phenomena like we have different beam lines here. I will describe in detail later. So 7 beam lines are ready in Indus 1, 5 are in operation, and 2 are under development. This is the Indus 1 hall where you can see a small storage ring, and this one is Indus 2 where more number of beam lines can be accommodated because it is a bigger source, and it gives you higher energy of 2.5 giga electron volt. This is the hall where all these equipments, all these beam lines and storage rings are placed. I'm talking about beam lines quite often. So I should tell you what is a beam line. A beam line is, it looks like a pipe. Like you can see here, it looks like a pipe inside which you have photons. From the storage ring, electrons are moving. If you bend their path, they will be just accelerated or decelerated, and they will emit photons. And from that photons, you just travel them inside this beam line, inside ultra high vacuum, and they will reach your experimental station. So we are getting a broad spectrum, but we are doing some specific experiments like we are doing photoelectron spectroscopy, lithography, or other small angle X-ray scattering. For that, you need different energies. And to use them, we have optics, we have crystals, and we have toroidal grating monochromators to select the energies. You all know about the grating. So these are just special kind of gratings. From that, you select the energy, and that desired energy will be traveling through the beam line, and it will reach to your experimental station where different kind of experiments can be performed. Uh, Whenever you come for an experiment, it is very important that you know what parameters you are getting, what energies will you get at that particular instrument or at that particular beam line. So here I have just summarized some of the parameters. Indus 1, as I said, it is a small source, so you can get far infrared to soft X-ray region of the wavelength spectrum. But Indus 2 has higher energy, so you can have even hard X-ray energies for your experiments. For example, if you are going for diffraction experiments, you need wavelengths that are comparable with your lattice spacings. So you need hard X-rays for that because their wavelength is very small. So you can select whatever energy you want. And these are the curves where you can see the spectral brightness. Indus 2 is much more brighter than Indus 1 because in combination with the bending magnets where we are bending the electrons, we also have some undulators and wiggler-like devices. And these are the beam lines of Indus 1 and Indus 2. Basically, they are divided in some sections. Like you can have scattering beam lines, you can have imaging beam lines, lithography beam line, and some other beam lines are yet to come there. In Indus 1, you can work on high resolution vacuum ultraviolet radiation. With that radiation, since it has very small energy, you can study the absorption phenomena in gases. Or if you have liquids, then we have a specially designed cell for that. So you can just place your liquid there, you can vaporize it, and in gas phase, you can see the the absorption phenomena in these gases. Other beamlines, as Dr. Ramjan said, we have PES beamlines. One is angle integrated photoelectron spectroscopy, and another is angle resolved photoelectron spectroscopy, on which I am working there. Then we have X-ray reflectivity beamline, so that you can study the reflectivity of multi-layers, thin films in as per their absorption edges. Then we have photophysics, where you can again see the absorption of various kind of materials. One beamline is FTIR, which has a laboratory source as well as synchrotron source for performing IR spectroscopy measurement to see the bonding between the different elements in your sample. And this beamline will be coming soon. And next beamline, photoabsorption, is also under development. Well, I'm just giving an overview, but you can see the details of these beamlines on this website, where you can see whatever is going on there, what kind of experiments they can perform. You can contact the concerned scientist, write a proposal, discuss with them, and then you will be allotted a beam time. And similar to Indus 1, in Indus 2 also you can perform various experiments. Like you can have X-ray absorption spectroscopy, for which one soft X-ray absorption spectroscopy is there. Two beamlines are more, which can give you scanning exacts and just the one-shot exact spectroscopy. Lithography beamline is there, where you can make very small structures. You can make gears which are in micron size. You can make nanoscale structures. You have imaging beamline, which can be used for measuring the biological samples, as well as you can measure rock samples, so to see their composition and how they were formed. I myself have done several experiments there. One more ARPES beamline will be there very soon. It's under development right now, but initial results have come out. You can also perform X-ray diffraction under extreme condition like high pressure and high temperature. These experiments can be planned there. And several other beamlines are there, like small angle X-ray scattering and X-ray fluorescence, which can give you composition of the sample. We also have two diagnostic beamlines where beam parameters can be measured. Their horizontal and vertical divergence, beam acceptance, all these can be measured. So I just want to tell you what I'm performing these days. I'm working on the angle resolved photoelectron spectroscopy beamline of Indus 1, which belongs to BRC Mumbai. This actually Dr. Ramjana has already told you about photoelectron spectroscopy. So it is based on photoelectric effect, which is when you incident some light on a material, and if its energy is beyond a threshold energy, then electrons will be ejected from that material. We capture those electrons, and then we understand from which element they are coming. So you can have information, like you can have elemental composition, chemical state, electronic state, and you can have band alignment at the interfaces. And with advanced measurements like resonance photoemission and angle resolved band structure mapping, you can have a complete picture of electronic structure of any material. You can plot the famous EK diagram if you have gone for angle resolved photoelectron spectroscopy measurement. And for these kind of measurements, as Dr. Chaudhary said, we can have laboratory sources like aluminium and magnesium K alpha sources, which will cover most of the core levels of all the elements, and some valence band features can also be seen. Because it has high energy, so it reaches core level more. And if you have soft X-ray, like from the Indus 1 source, then you can have a surface sensitivity. In this universal curve, if you see, on my beamline, we have 10 to 300 electron volt energy, which is very less. So your electrons will have very less kinetic energy, and so their mean free path will be very small. That means signals will be measured only from the surface. That makes it surface sensitive technique. And if you have hard X-rays, then you can probe more. So I'm not going into detail because he has already talked about it. With this angle resolved beamline, angle resolved spectroscopy beamline, you can perform various kind of measurements. We have an energy range of 12 to 300 electron volt that can probe mostly the valence band and as well as some core levels of any material. So you can study them both. And we have 2D CCD detectors, so we can measure the 3D map of band structure. We have angle integrated as well as angle resolved photoelectron spectroscopy, and there are several facilities. You can just scrap, sputter, cleave, or heat your samples in situ. So whenever you take one sample, we will scrap it inside so that it is clean, and then in situ you can transfer it to the experimental setup. And we have a low temperature facility where you can cool down to 6 Kelvin so that any phase transition can also be studied, because you will be going from room temperature, you will record your spectra there, you will go down to different temperatures and then you can record. We also have a helium discharge lamp to record the valence band feature and to record the work function of your sample. And for single crystals, we have lead and OJ facilities so that before recording the band structure, you can understand which crystal direction you want to probe for band structure measurements. An additional facility on this beamline is the attached PLD chamber. So you can grow your films, and without breaking any ultra high vacuum, you just transfer your sample from PLD chamber to the beamline and do your measurements. That will give you the most clean environment ever. And with this facility, single crystalline films can be grown, and we are just doing some trials of HF photo thin films, which have been grown to be highly oriented. Epitaxy will be a later step in that. And with this beamline, we can do valence band and core level studies, resonance photoemission, and band structure measurements. That too from room temperature down to low temperature. And these are the photographs of the beamline. Here, this is the beamline pipe from which we get the photons of desired energy. And this is the ARPES chamber where we perform the measurements. This is another view where you can see the sample cleaning chamber and ARPES chamber, sample cleaning chamber, and there is one load log chamber which is connected to the PLD. And here we have Nd:YAG laser to grow our thin films in situ. These are the some recent results which we got from the beamline. On the left, you can see that we can also record valence band spectra on bulk samples. You can sputter them or you can cleave them if they are single crystal. So we sputtered them and very clean features were obtained, because all this time the beamline is maintained under around 10 to the power minus 9 or 10 to the power minus 10 millibar, while our experimental station is always maintained at around 3 into 10 to the power minus 11 millibar, so that electrons will never be lost. And similarly, on the right side, some thin film measurements are there. We have grown heterostructure thin film inside the PLD system, and then we recorded the band offset measurements. These are from our user group, so I'm not going into detail. As I said earlier, I'm working on some nanomaterials for which I'm using laboratory based as well as synchrotron based sources of Indus 1 and Indus 2. I have grown terbium doped cerium phosphate nanomaterials using chemical synthesis method. These kind of materials are very useful. If you have a bulk cerium phosphate, then that material is very useful for nuclear waste management, and they also show some luminescence, and they can be used in medical field and all other applications because they are very highly stable. If you say about thermal stability, yes, they can go to 1800 or 1900 temperature without any deformation. They are chemically also stable. One more important thing of this material is that it can accommodate whatever doping you are giving to it. So if you dope it with terbium will go inside its lattice and it will sit there very beautifully. And using this terbium doping, you can just tune its luminescence properties. Like cerium phosphate gives you luminescence, which is not much enhanced and it will be in UV range. So UV range luminescence is not much useful. But if you are doping it with terbium, there will be some energy transfer from cerium to terbium. In that case, terbium will give you very highly enhanced luminescence and that too in the visible range. I will show you later. So in case of terbium doped cerium phosphate, if I further go down to nanomaterial, then I have an additional parameter of particle size tailoring. So as we tune the particle size, we will be having different kind of properties that also can be studied. That's why I worked on this material because it was very interesting from luminescence point of view. And I have done different percentage of doping of terbium inside cerium phosphate. That was 5, 10, 15, 20. So that luminescence enhancement and then quenching can also be studied.
Sorry
As
for
I said,
disturbing, madam. Can you? We will be grateful if you can limit your presentation, conclude your presentation in 5 minutes.
yes, sir, I will do that.
Okay.
So before going to any synchrotron-based source, it is better that you do all the laboratory-based measurements before you plan for beam time. Otherwise, beam time will be wasted if your material is not pure or if it has some impurities. So I first performed X-ray diffraction measurements where I saw that my samples were initially hexagonal in crystalline structure, which is not a stable phase. So to make them stable, I annealed them under nitrogen environment because I did not want cerium 4 plus to appear that quenches the luminescence. So I annealed them and I saw that they are perfectly monoclinic in crystalline structure and they were highly pure. No other phase impurity was seen. So I could go to the beam line. I did some measurements with very high flux, very high signal to noise ratio, higher resolution, and I saw that these materials are highly pure and no other chemical impurity even in very small amount is present. But with doping some kind of strain was seen. So I'm still analyzing the data and how this strain is changing with the doping concentration. Then I performed some laboratory-based compositional measurements where FTIR showed some bond formation where PO4 tetrahedron was seen, which is a characteristic of phosphate group. Then EDEX measurements were done so that I could see that there is no other chemical impurity in my samples. And before going for small angle X-ray scattering, I did some transmission electron microscopy measurement so that the shape and size of these material can be seen. Because I was saying that, okay, I did some nanoparticle growth. But no, they were nanowires, as you can see here in pure and 5% doping. And when I increased the doping percentage, there was some agglomeration of the nanowires. They are still nanowires, but here flower-like structure was seen. And in the high resolution TEM images, very nice arrangement of the atoms was seen, from which I could extract the D spacing, lattice spacing, which was matching with the monoclinic structure. And since these materials are very efficient luminescent materials, so I studied their luminescence as well. When I doped with terbium, then visible range emission was seen and okay, I had just given the electronic transition that are responsible for the luminescence. I'll take just 1 or 2 minutes. Uh, then I finally performed the beamline measurements. I did some photoelectron spectroscopy measurements where bulk as well as nanoparticles were measured. Here one drastic feature was seen. I annealed them under nitrogen environment to reduce the amount of cerium 4 plus. But from PAS, I could see that I have cerium 4 plus oxidation state in domination. Why is that so? Because my samples are highly luminescent, so they should not have it. So that's why I had to plan some more experiment with the exact beam line. And when this was done, I also took one standard cerium oxide sample, which showed the contribution from both cerium 3 plus and 4 plus oxidation state. But in case of my samples, I could see only cerium 3 plus. There was no cerium 4 plus seen in these samples. This is because PES is highly surface sensitive. So it is possible that at the surface, cerium 4 plus has formed, and inside the sample, cerium 3 plus was there. So that was quite interesting feature. So I could explain why my samples are photoluminescent while there is some amount of cerium 4 plus. And as I said earlier, TEM measurements formed a basis for small angle X-ray scattering measurements, where I could see the average diameter and length of the nanowires. That was both in nanometer, and the diameter was quite small. So that means my nanowires have formed all throughout the samples. And this is my final slide. I'm trying to analyze the resonance photoemission in terbium doped cerium phosphate nanowires. As I has already explained by Dr. Chaudhary, I'm not going into detail. In this case, if I have cerium 3 plus, then this feature will be enhanced with energy. And if I have cerium 4 plus, then a side feature will be enhanced if I go to higher energies. I could see cerium 3 plus enhancement. That means my cerium 3 plus is contributing in all these luminescence and other properties, not the cerium 4 plus. So that means I could successfully grow nanowires with cerium 3 plus oxidation state, which is very highly desirable for luminescence applications. So finally, I could see, I could tell you about the synchrotron radiation in detail. And I have performed some laboratory-based and synchrotron-based experiments. So it is always requested that whenever you come for the beam time, you prepare your samples first, and then you do some laboratory-based experiments, so that your beam time will be highly utilized. You check their purity, you check their applications, and then you come there. For example, in this case, I could grow nanowires that were highly single crystalline, they were highly pure, stable, and also highly luminescent. So their energy transfer mechanism is the topic which I am right now trying to analyze. And in the end, I would just like to acknowledge the persons who were always with me during all these experiments and during our daily operation of the beam line. First of all, I would like to thank my head, Dr. S.N. Jha, and my group of scientific officers, engineers, and assistants like Mangla, Yogesh, and Ankur, Ashutosh, Babita, Bhatt, and Sahu, who are always there with me, and synchrotron radiation source team, which is responsible for the maintenance and operation of whole of the Indus source. And in the end, I would like to acknowledge my users and their groups, because otherwise I won't be able to work on different kind of samples and learn the things. Thank you very much.
Thank you, Silpa. Thank you for the really nice presentation. And this is another facility which we are started using of the RRCAT in the coordination with the Jhaji. So we are really thankful for all the support, all the collaboration people are offering to us. Due to shortage of time, I am extremely sorry we are not taking the questions. We take the question from the audience and we mail you, because already it is going to be 1:30 and our next session is from 2:30. Sorry, 2 o'clock. So really thank to all of you for giving your time and delivering your talk. Thank you very much. So Pooja, next proceed please. You are muted. Pooja, you are muted.
Thank you, sir. I thank all of you for being present at the morning session of the event and making it a success. I remind all of you that there will be an assessment after today's technical session, and the link of the assessment will be provided at the end of the session. Now we will take a short lunch break and we will gather again at 2 p.m. sharp for the post-lunch session. Thank you all.
mic to Anshay. Abhishek, can you hear me? हाँ अभिषेक हाँ अभिषेक
So can we start now?
Yes, from my side, I'm ready.
Just wait a minute or two because Sinha sir is coming back, I think. So then
Okay.
we'll start.
Yeah. Abhishek,
Yes, sir.
now we
Yes,
start.
sir.
Good
Yes, sir.
afternoon, all.
Okay.
Lalitji, please make Dr. Kavita Sharma also co-host.
So
Ma'am, should
welcome
we start?
Professor Hafsaz again to Amity Institute of Nanotechnology.
Good morning.
And it is our pleasure to have you as a speaker. So
Okay.
we can start now.
Okay. So welcome back to the post-lunch session. So in this session, we have 4 talks. So first one by Professor Hans Hofstad from University of Göttingen. So he will be talking on ultra low energy ion implantation of 2D materials. And then second one by B. Sundarval from IGCAR Kalpakkam on ion beam modification of nanomaterials. And third talk will be by Dr. T. Mohanty from Jawaharlal Nehru University. She will be talking on control surface electronic modification of 2D materials by irradiation engineering. And a last talk by Professor Alok Kanjilal from Shivnadar University. He will be talking on ion beam dosimetry of self pattern alumna films. So now I request to Abhishek to introduce our first speaker, Professor Hans Hofstad.
Thank you, sir. Good afternoon, everyone, and welcome to the second technical session of the day 3 of e-workshop on energetic beam technology from materials engineering to diagnostic. Myself, Abhishek Mishra, student of BTech Nanotechnology program, welcome you along with our session coordinator, Dr. Sambhunath Behra and Dr. Kavita Sharma. I would like to mention to the attendees that you can submit your questions in the Q&A panel or chat box, addressing them to everyone. We'll be reading out your questions in the Q&A round at the end of the session. Moving on with the event, let me call upon our first honorable speaker for the technical session 2, Professor Dr. Hans Hofstad, University of Göttingen, Germany. Professor Hofstad completed his PhD and habilitation from University of Konstanz, Germany. He also did his postdoc from University of Konstanz, Germany. He is a proud recipient of Dernier Research Award and he is a member of the Senate of University of Göttingen. He has hundreds of publications to his credit in high impact journals. Today, he'll be talking about ultra low energy ion implantation of 2D materials. I humbly request you, sir, to kindly conclude your talk in 45 minutes, which will be followed up by a 10 minutes Q&A session. We welcome you, sir, and the stage is yours.
Yeah, good morning, everybody. I hope you can see the slides and you understand me. Is this okay?
Yes, sir.
Okay, so the title of my, so it's a pleasure for me to give this presentation. And the title is Ultra Low Energy Ion Implantation of 2D Materials, graphene and other low dimensional materials. And the special topic is actually the first two words, ultra low, which is an energy region which is very unusual for typical ion implantation issues. So there are, I've listed several members and former members of my group who participated in this work. And the outline is that I'm discussing general aspects of ion implantation and doping of 2D materials, some predictions by molecular dynamics and Monte Carlo simulations on the ion implantation. And then I show, let's say, our technical realization and some aspects how to do ultra low energy implantation of mass selected ions. And I show a number of examples how we characterize this special implantation process. And some examples are given for doped graphene and molybdenum sulfide. And at the end, I will discuss some new implantation options which we have recently developed. So we do the implantation since several years, and it seems that our system is more or less the only one in the world which is able to go to these low energies and do implantations in a controlled and clean way. And because of that, we cooperated with many groups throughout the world. And this is just a list of people who came to Göttingen and either brought their samples or sent us their samples and asked for implantation of these 2D materials like graphene or molybdenum sulfide or selenide. So what are the options to get doped graphene 2D material? First of all, there is a chemical route, which is chemical vapor deposition. There are several papers describing this. Then you could, well, also maybe a chemical route, use arc discharge of graphite in the presence of some nitrogen or boron containing gases. So that's a, let's say, gas phase synthesis of doped graphene. You can expose graphene to a nitrogen containing plasma. You can do ion irradiation or ion implantation of graphene, but so that this has been done with energies down to 50 or 100 electron volts, which is still a bit too high. And then there are papers about higher energy, which is still considered low energy ion irradiation, 30 keV. And typically what you see, this is the Raman spectrum, which is shown here. And the red arrow indicates the so-called 2D Raman line. This actually is a signature of pristine graphene, which is the spectrum at the bottom. And if you do the irradiation with moderate or low fluence, you destroy actually the graphene and you get some significantly damaged, let's say, graphite structure. So the 2D Raman line disappears, which is the 2D line is a signature that you still have the 2D material present. So 30 kV ion irradiation is definitely significantly damaging and not suited for doping. So we had the idea to do an ultra low energy implantation, which could be considered as one billiard type collision. So here the red low energy ions are coming in, maybe nitrogen ions. Then you have your 2D material, graphene, and you have one billiard collision so that you recoil one carbon atom and you replace it by the incoming ion. So that's the idea of ultra low energy singly charged mass selected ion beam implantation of 2D materials. So you get recoiled carbon atoms, you hopefully replace the carbon substitutional. And we did the first measurement together with a group in UK and now Ireland. So we used graphene deposited on TEM grids, which are self-supporting films. And then you could do a high resolution TEM analysis. And the red dots you see here in the image are actually substitutional dopants of either nitrogen or boron, which could be analyzed, which I show later on. So the process actually works. And from the image, you see that it's actually a crystalline 2D material after implantation. There are predictions from molecular dynamic simulations. This has been done also for ion impact. And the summary of these studies is that you can get a substitution without creating some damage or single vacancies in graphene if the energy is definitely below 50 electron volts. Otherwise, you get some vacancies and damaged graphene, and for very low energies also you get some add atoms, which is not really a problem, but you want to have the substitution without getting a vacancy, which is here on the left side, the image B, which shows you typically the energy spectrum where you should work. So below 50 electron volt would be the good idea. And we use Monte Carlo simulation, binary collision approximation based on like the popular TRIM software. We use a related software, which is called SD-TRIM-SP. And there we can at least estimate the concentration of carbon and boron atoms after implantation, the fluence dependence, sputter yields, and the energy distribution of forward recoiled or forward sputtered carbon atoms. So this gives us a first idea about the efficiency of a low energy implantation. So this is an example of such simulation showing for 20 electron volts boron incident on a 6 angstrom amorphous carbon layer. So these simulation only consider amorphous material. 6 angstrom would correspond to a double layer of graphene. Okay, from this we get an idea how many ions could be implanted in a 2D layer, how many ions are recoiled into the substrate or backscattered. And we did this for several systems and several dopant atoms and different dopant energies. And our best choice for doing this implantation is 20 to 25 electron volts for the incoming ions, either boron or nitrogen or fluorine or some other ions. We could go down to 10 or 15 electron volts, but that's, as a first guess, quite nice. So how do we do this? So we use a conventional ion implanter, which is shown schematically here. It has an ion source where ions are accelerated to 30 kilovolts. Then we have a 90-degree magnet for mass selection. And then we have some beam ion optics to guide the beam. And then we guide the beam into an ultra-high vacuum chamber, which is here. And there we decelerate the beam electrostatically to very low energies. And actually, if the ion source is at 30 kilovolts, we bias our substrate to a bias minus, let's say, 20 volts below the 30 keV, defines final ion energy. And the ion optics can be done in a way that you get a reasonable homogeneous irradiation of your sample area. And we can measure the beam current very precisely. We can change the temperature of the sample and so on. And the sample holder is shown here. And this is a view not very nice through a window showing the deceleration stage, which is very compact. And the deceleration is done over a distance of a few centimeters. So we use a normal to a UVHV chamber, ultra-high vacuum, and we have an electrostatic deceleration system. This is how it looks like. You see it's homemade. It's not actually the ion implanter itself is, the basic is from high voltage engineering, but everything else is just a homemade system. And we've also modified ion sources and so on. This is just the center image shows the simulation of the deceleration, and the red trajectories are the ions. And you see that you can decelerate the ions without focusing or defocusing them, and you get a very homogeneous irradiation of the substrate. And we tested it by depositing carbon atoms on the substrate, and you can see you can grow carbon films which are very homogeneous, except here this outer boundaries which look like the rim of a crater, but otherwise the center part is very homogeneously. Since we have a 90-degree mass selection magnet, we can do mass selected ion implantation, which is typical requirement for any ion implantation system. So this is the setup which we use, and the ion sources are commercial ion sources from high voltage engineering, which is the so-called hot cathode, hot filament hollow cathode source, where you ignite a plasma here in the center and you extract the beam to the right, and it's heated with a tungsten filament, and you feed in some gas or some solid material. For example, in the gas stream, you can put some chromium powder, which is shown here, and then you can get chromium ions. So that's a rather versatile, tiny ion source. The total length, what is shown here in the red circle, is maybe 5 or 6 centimeters. So it's very compact. And you get a point-like ion beam, which can be very well focused. And to see if the implantation actually works, so we implant into some test samples or graphene or some other materials. One of our test sample is diamond-like amorphous carbon films. And then we use Auger spectrometry, a surface-sensitive technique, where we measure the Auger electron intensities. And this is shown here on the left image. And for chromium implantation, we see here in the red line the characteristic signatures of Auger electrons from chromium. So we actually have implanted chromium very close to the surface. And the chromium can also be seen in conventional Rutherford backscattering spectra, which is shown here, done with about 900 keV helium ions. And we see here the backscattering signal at 600 keV from chromium close to the surface of our diamond-like film. So this actually works, and we can quantify the implantation dose of chromium. So these are typical characterization analysis which we do after the implantation. We could add selenium to our ion source, and then we can get a selenium mass spectrum, which is shown here. And we choose selenium 80, the highest intensity for implantation of, let's say, selenium dope, to create selenium doped molybdenum sulfide, for example. And so since it's mass selected, okay, our samples are doped with selenium with mass 80. Or if we use boron, it's doped with boron with mass 11. And we could also get a good suppression of neighboring masses to avoid contaminations. For example, we can implant isotopically pure manganese 55 and separate it from contaminations of iron 56. We can implant sulfur 34 or phosphor 31 to avoid contaminations with oxygen 2+ ions. So it's quite, the implantation process is, as for any implantation process with mass selection, quite clean. Some examples also: Auger spectra for that's a graphene on a nickel film on silicon, where you see a tiny signal of boron, which we actually implanted, and an even more tiny signal here from nitrogen. So which shows it's difficult to detect boron and nitrogen doped graphene with Auger, but it's possible. So the intensities are weak, but it's possible. It's more clear if we dope with manganese. So you clearly see the manganese Auger signal, and also you see the iron Auger signal. And here are the implantation fluences, few times 10 to the 14 per square centimeter into a 2D material, for example. So this can be analyzed. And also RBS is a very nice method to characterize these materials. To detect iron, to detect selenium, and to detect phosphorus with different implantation fluences. So RBS is a quantitative technique, so this is very useful to confirm, let's say, our ion fluence measurements or integrated ion current measurements during implantation. Now there are some elements which would be interesting for 2D materials, but they are difficult to produce in an ion source. So here is the conventional ion source based on a modified high voltage engineering, hot filament hollow cathode ion source. And we modified, so we made it a little bit longer and added some sputter target, which can be biased to, let's say, kilovolt biases. And there we can sputter off high melting point and some tough materials, as it shows here in the title, like iron, molybdenum, tantalum, tungsten. So they are high melting point or low vapor pressure materials. And in this way, we can also get access to these interesting but difficult to produce ions in an ion implanter. And this is that it works, shown here, an Auger spectrum, where we see actually the iron signals, and the iron was implanted with 20 electron volts, and we even get, let's say, microamps per square centimeter, which is way sufficient for implantation of 2D material. So it takes about 2 to 3 minutes to implant a very high concentration into a 2D material. Also, PIXI, X-ray analysis with protons is interesting to identify the ion and contaminations. And you see, except for the ions and the silicon substrate and the argon from the air, we see actually no contamination. So that's a very clean and pure implantation which we can achieve. This is a mass spectrum of our ion source where we produce molybdenum ions, molybdenum plus with different masses. And we could select the molybdenum 98, the most intense mass, for implantation, where we get at least 70 nanoamps, which is very sufficient to do implantation of 2D materials. So this shows that we, because of the mass selection and because of this new development of the ion source, we can also have access to this, let's say, odd high melting point ions like molybdenum, tantalum, tungsten, and so on. Also, the molybdenum is seen in the Auger spectrum and also in the RBS spectrum. And you see the spectrum is sensitive enough that we actually see a background from arsenic doping of the silicon. And here at the surface implanted is the molybdenum, and this is implanted with 20 electron volts. Now some examples, and let me start with nitrogen and boron doping of graphene. So this is the most interesting and most easy case to do regarding the implantation, and also there are very nice technologies based on transmission electron microscope to characterize it. Nitrogen and boron are easy because it's an almost similar mass to carbon. So if you consider this one billiard collision, that's the ideal case just to replace carbon by nitrogen and boron. Okay, we did the first irradiations of graphene with nitrogen and boron, and that was graphene grown on silicon carbide in ultra-high vacuum condition. Then we took the samples out, put it into our implanter. So the transport was under ambient condition. That's not, seems to be not a problem. And then we can implant it. And then we use scanning tunneling microscopy to characterize the electronic signature of the graphene. And we can identify dopants like here. typically you see some sort of three-fold symmetric structure, which is related to the threefold symmetry of the graphene. And this is also the case for boron. And you see, if you compare a pristine graphene on silicon carbide undoped, this is the upper right image, and you compare the nitrogen doped, you see the many threefold symmetric spots, which is the electronic signature of a nitrogen dopant in graphene, which gives an impression about the dopant concentration we get. So this could be of the order of 1% or even a fraction of percent. So you can use scanning tunneling microscope and just count the number of signatures here, and then you can quantify the implantation concentration or the dopant concentration which you have achieved. This is once again this situation, pristine graphene and nitrogen doped graphene. There you see a lot of features, typically this electronic response for substitution. Nitrogen gives you some threefold pattern which extends over many lattice spacings of graphene. So the scale here is 2 nanometers. Okay, then we did implantation into freestanding graphene, which were deposited on TEM grids, tiny copper grids. And these samples were then transported to a high-resolution electron microscope in UK, near Manchester. And they were analyzed, and with a method which is called high-angle annular dark field image. And you see the graphene lattice. This could be resolved in high resolution TEM. And you see some structures which have a different intensity, either brighter or darker. Here it's brighter. And in the dark field image, what you see actually is the contrast based on the atomic number of the atom. So that's the atomic number squared contrast. So if you mark these atoms which are a little bit brighter and color them, like here, the red points, then you actually see the substitutional nitrogen atoms. You see they have a larger C compared to the carbon because they appear brighter here. So the scattering intensity is larger. So this is the direct evidence of substitutional nitrogen doping of graphene by ultra-low energy ion implantation. And you can look a little bit closer, and you also see that there might be some vacancy defects. So it's not everything is perfect. Here, the bright atom in the in this gray image shows the nitrogen atom and a vacancy complex, which can be identified here. You see, this was published in 2013, so this shows how many years we are working on this ultra-low energy implantation process or technology. So you can do a little bit more elaborate and more detailed analysis. So this is once again a high resolution image from an electron microscope showing the graphene sheet, and here you see there is a darker atom, so this is darker atom means lower atomic number, and so this is the contrast you see for boron compared to carbon. Boron has a lower atomic number than carbon, and then you can do at this spot, which is highlighted here, an electron energy loss spectra, and you look for the characteristic energy loss for the boron K line, and it can be actually seen here. So this energy regime over here, this energy loss occurs only here where you have the dark atom. So this clearly shows that you can identify a substitutional boron atom in graphene with atomic resolution. The same can be done with nitrogen, and here you see the brighter spot, so that's a heavier or an element with larger atomic number, and you can look for the nitrogen K energy loss, and you see that this only occurs here at the position of the nitrogen atom. We did also some angle resolved photo emission measurements together with a group in Mumbai, And so this will be published soon. And with this method, you can actually measure the Dirac cone of graphene, and from the crossover of the Dirac cone with the binding energy on a reference for pristine graphene, you can identify whether it's, let's say, N-type doped or P-type doped, in a sense that you shift the Fermi level. And on the left image, you see nitrogen doped graphene. And here the crossover is at negative binding, at binding energy, let's say 0.7 eV. And for boron doped graphene, the crossover shifts upwards to negative value. So you actually see that on nitrogen and boron doping, you can actually shift the Fermi level in graphene, and it can be measured spectroscopically with angle resolved photo emission spectroscopy, which is shown here in two examples for boron and nitrogen doping. So the electronic doping in terms of in the view of shift of Fermi level actually works. And okay, maybe I skip this. You can actually focus to a certain point, which is either the boron or the nitrogen atom. The red and the blue arrow indicate this, and you can do energy loss take energy loss spectroscopy and measure the spectra, and you can analyze them very detailed by going away atom by atom from carbon 1, 2, 3, which is a small image here in the center, and measure the yield spectrum. And you can actually see how the nitrogen atom influences the electronic structure away from the nitrogen atom to the, let's say, the third next near neighbor, carbon 3. So there are some differences in the energy spectra which can be analyzed, and which gives an idea on how the electronic perturbation of a nitrogen atom, how far the electronic perturbation of a nitrogen atom goes, and it can be actually seen up to maybe the third nearest neighbor to the nitrogen atom, which is a very difficult, complicated yields analysis and requires a lot of experience analyzing these spectra. We also found out that graphene is relatively stable, but not too much. So if we do an TEM analysis, then we see that the electron beam actually dynamically changes the image. So here we have a nitrogen doped graphene. So the nitrogen atom is the bright atom marked by the red arrow, and there are defects nearby, and upon electron irradiation, this defect structure changes here. So the substitutional atom in the upper right part of the image remains the same, but the defects somehow change dynamically. So which can make a picture. These are the cartoons in the center showing that you might have dynamic changes in the graphene, in the doped graphene, induced by the transmission electron microscope itself. So you have to be careful for that. We did also some analysis of phosphorus doped graphene. And actually that is an interesting paper which we did together with a group in University of Vienna, Austria. And this is a high resolution TEM picture. And we actually detected one phosphorus atom, so the green one. The red marked atoms are silicon atoms, which are some contaminants, but the green one is a phosphorus atom. So this is one identified phosphorus atom, and this can be analyzed. And so the summary of the analysis, that it's a substitutional phosphorus atom, but it's somehow buckling out of the surface. So the image D shows actually the most likely geometric structure of a substitutional phosphorus atom. And to get to this conclusion, you have to do simulations of the structure, and the simulations lead to simulated electron energy loss spectra. And these are shown here. And the blue curve is just the simulation for a buckled structure, and the gray part is actually the measured yield spectrum. So there's a significant difference compared to the flat. So it's most likely that for phosphorus, we have such a buckled substitutional incorporation of phosphorus. Okay, so this is only one, for only one atom we found here, the phosphorus characteristic energy loss. The others are for silicon. And this is a paper which was written based on results obtained for one single atom, phosphorus atom. But okay, the analysis is quite unique, and this can be done, but okay, should be repeated to get a better statistics on the behavior of phosphorus in graphene. Now let's start with the more complex 2D materials, which are the transition metal dichalconides, molybdenum sulfide, tungsten sulfide, and molybdenum selenide. And actually, there should be some image which are not shown here, but here you see some high resolution image taken of such a sample, and you see different structures, some defects, some dumbbells, and so on. So you can incorporate selenium in molybdenum sulfide in a way that sometimes you get some defect structure with a 6-ring structure, then some dumbbells with 2 and selenium and phosphor, and they can be analyzed. And unfortunately here, the PDF doesn't show this. So you can actually analyze these, what is shown here in the this ellipsoids, and you look for the intensity changes if you go along the arrows A, B, C in the TM section. And if you look here on the bottom, let's say take the picture C, the center part is 2 more or less same intensity, and the left and right one is a lower intensity. And this is indication that we have replaced selenium on sulfur side. So that is the doping of selenium. So also here, these dumbbells, you see there's one brighter and one more darker spot, and the brighter one is actually the selene atom, which can be analyzed with some effort and comparison with simulations, which shown here on the top. And you can just draw some intensity profiles along the red and green and blue lines and analyze them. And then you see here what is a sulfur atom with a lower intensity and what is a selenium atom with the higher intensity in these images E and F, which are then the scans along the blue, red, and green line. So this can be done also with electron microscopy to identify that we have selene substituted on sulfur sites. Also shown here some simulations of a monolayer molybdenum sulfide, and these simulations can be compared with the measured profiles, and then we are quite sure that we have substitutional selenium in molybdenum sulfide. We can also do hot implantations of selenium or other materials in these 2D materials, molybdenum sulfide. And there's one feature, so it's not always a good idea to do a hot implantation. It only just shows we can do implantation in 2D materials at elevated temperature. And what we see here is the green line, the intensity grows here. This is a Raman spectrum. And this green line is a signature of a molybdenum sulfur selenium alloy signal. So upon going up in temperature, you are going away from the 2D material to something which is more a ternary alloy. And this can be seen, and the ternary alloy actually has the negative effect as a function of temperature, that a PL intensity which exists for the 2D material actually disappears. So the PL intensity from the shown in the red curve for low temperature is still there, but then an elevated temperature it disappears. So in here we see actually a damaging of the molybdenum sulfide, and the damaging is most likely due to an alloy formation at elevated temperature. So there is the option to do implantation at elevated temperature, but it's not always the best choice to do this. Now, maybe the remaining time, few minutes, just to show you what we are working also on and what is the requirement for ion implantation, that you can do a lateral selective implantation. In conventional ion implantation, this is done by implantation masks, which polymer resists, which are deposited and then which are removed afterwards. This is difficult in 2D materials, so you have to choose another option, and we tried to use an electrostatic mask. And this is shown here, some ion trajectories, and we have here the 2D film at the bottom, and we have electric contacts there, and we bias the contact at different bias voltages, maybe 30 kilovolts in the center. So the ions would arrive at 0 energy and are reflected, and at minus 20 electron volts over here. So we get, let's say, a certain area where we do not get implantation and a certain area where we get implantation. So that is the idea of electrostatic masking. We did some simulation how efficient this will be, and we did some measurement by implanting, for example, selenium into a diamond-like amorphous carbon, and the RBS spectrum actually shows here the variation of the selenium concentration as a function of the distance from a contact stripe at different bias voltage. So it qualitatively shows that we can do this selective implantation on a certain area of a 2D material using this electrostatic masking. So this is also a feature which we can do, and the sample holder actually shows with these tiny triangular pins where we contact the electrostatic masks, and then we can do the implantation and get a lateral selective implantation on the 2D material. Okay, to summarize, there are some keywords. So we have developed ultra low energy mass selected ion implantation for controlled doping of graphene. That's where we started, and ultra low energies is typically 10 to 25 electron volts, and the typical implantation doses or fluences are at most 10 to the 15 per square centimeter. 3 times to 10 to the 15 would be 1 atom per surface atom of a 2D material. So that would be, if we have a complete incorporation, 100%. We can implant under UHV conditions. We can get sufficiently high dopant concentration. We have various techniques where we can characterize our sample. Quantitative analysis is done by RBS and NRA. And we have developed certain features to implant exotic ions like molybdenum and high melting point materials. We have developed this electrostatic masking, and we can do hot implantation. So now we have a very versatile system for ultra low energy implantations with many available ions which can be used for various 2D materials. So with this, I'm at the end of my talk, and I hope I'm in time. Yes, and I thank you for your attention, and I'm happy to answer questions.
Okay, thank you very much, Professor Hans. So it's nicely we explained about this low energy ion implantation in graphene, and also the 2D materials, other 2D materials like MOS2 and tungsten disulfide. Also, and in addition, also we have explained about the high Z material, so, like iron, selenium, and how to dope them. and explained both by experimentally and theoretically. Thank you very much. So now, if there is any questions from the panelists.
Really amazing talk, Professor Hofsas. Especially the ultra low energy, which is basically you have taken the mass selected ions to do the control doping in the graphene and the 2D materials. It is a new way or the new path for the controlling the 2D materials and the doping on that one. The moment we are talking about the MOS2 or TiSe2, basically we have shown the result with ion irradiation. Typically, what will be the doping concentrations we expect or we can dope in given material without disturbing the structural deformation?
So it's not possible to disturb the structure completely. So, but you can try to minimize damage. So what you see here in the 2D materials, so there is always damage. So there are, you see here in the left image some vacancies. You have these dumbbells. You have here more or less in a little bit in the center this 6-ring structure where you have some sort of accumulation of implanted selenium atoms. So you cannot avoid it, but you can minimize it. And the options you have is to vary the ion energy in a certain way and maybe the temperature. The temperature is often not, maybe you have to go to cold temperature, or the high temperature often lead to higher mobility and to agglomeration and alloy formation in these materials. The energy is a very sensitive point. For example, you have to have in mind implanting selenium into molybdenum sulfide. You have 3 components with 3 completely different masses. So you cannot avoid replacing or recoiling a molybdenum atom by selenium. The ideal billiard collision with identical mass partners is not existing there. So you have to think about a little bit what is the ideal energy. And so typically our experience is that you a little bit go to lower energies like 15 electron volts to avoid, let's say, recoil of molybdenum. You still get replacement of sulfur. If you go to too low energies, most likely it's more difficult to decelerate these ions. Let's say if you go to 10 eV or below, and then also many of these ions do not make a replacement collision, so they are just additivants and diffuse away. So there's a very fragile balance of ion energy and temperature and ion implantation dose to get the optimum results. Too high dose will definitely lead to damage.
Thank you.
So any other questions? Any other question from the panelists? There is a question from the attendee in the chat box. It's Rupam Mandal. So he's asking, how has the end changed the electrical behavior of graphene?
Can you just repeat it? So the sound was not.
How does the nitrogen doping change the electrical behavior of graphene?
So what you see here on nitrogen doping, so this is what you see here in the scanning tunneling microscopy. So with scanning tunneling microscopy, you're not actually imaging the topography, but the electronic response. So you're measuring actually current. So you see here in this right image, each bright signature with the threefold symmetry is a nitrogen atom, and it affects the electron current from the STM tip to the substrate, or in the other way. So you see an electronic signature of an individual nitrogen atom. And more detailed picture of what actually happens is, so you have a local perturbation of the electronic structure of graphene, and you have from this angle resolved photo emission spectra here, where you see the Dirac cone and the shift of the Dirac cone, which is, let's say, indicates a shift of the Fermi level. So by N-type doping or P-type doping, N-type doping is then with nitrogen, you can see that the Dirac cone is shifted from 0 to here 0.7 eV. So it's a definite clear shift of the Fermi level of the Dirac cone, and this changes the electronic properties of the graphene. And such a shift also occurs if you put the graphene on a substrate. So the substrate also has an effect that you get either a shift of the Fermi level either into the one or the other direction. But the doping does the same way. So you may use the doped graphene to compensate maybe such substrate effects to tune the position of the Fermi level in the graphene. So this is what you see as an electronic response. And maybe, well, not really electronic response is the energy loss spectra, which is also, you see the electronic structure in transmission electron microscopes, where you can also see, similar to this scanning tunneling microscopy image, how far is the effect of the doping, how many nanometers or angstroms do you perturb the electronic response by the doping. So this is clearly here seen in this STM images of graphene. But if we go further, let me see, one image, not the phosphorus, this one here. Okay, electronic structure means with electron energy loss spectrum, you measure, let's say, the valence band structure in the graphene, and this is modified by the dopant, and you can actually analyze it, how the additional electron supplied by the nitrogen atom influences the electronic structure of the neighboring carbon atoms. So this is maybe the points where we can learn about the electronic effect of doping.
Okay. So could you please explain me what is, do you mean by this freestanding graphene? Maybe I missed it.
The freestanding graphene, typically you have graphene on some substrate. So the commercial graphene is deposited on silicon or silicon oxide, or it's transferred with this Scotch tape method onto some, from copper to some substrate. So you typically have graphene on substrates. And one favorite substrate for people doing transmission electron microscopy are these so-called transmission electron microscopy grids, which are 3 millimeters in diameter, and they are grids with openings of, let's say, 2 by 200 micrometers. So these are commercially available. And you can transfer a graphene layer onto such a so-called TEM grid. And this tiny grid can be carefully handled. And there you have a lot of area where there is no substrate underneath the graphene. So it's just a freestanding monolayer of graphene or freestanding monolayer of 2D material. This can be analyzed in the transmission electron microscope, so you do not see the substrate. And these are the images which are shown here. So that's a high resolution TEM image of a freestanding nitrogen doped graphene film. The grayscale image is what you actually get from this high angle annular dark field imaging method. And the right image is just a color representation of the grayscale, where the nitrogen atoms appear as red dots in this image. But it's just a freestanding graphene layer doped with nitrogen.
So you doped it when it was on the substrate?
Yes, we can. Okay, you can prepare the freestanding films on these tiny
And
copper
then whether
grids,
you can,
3 millimeter
okay,
diameters. They are relatively stable, so you can send them by normal mail under ambient conditions from England to Germany. Then we can put it in our system, do the implantations. We have a sample holder where we can hold these TEM grids and then do the implantation, take it out, put it into the mail, send it to United Kingdom for the TEM analysis, and that's the result.
yeah,
So
that's nice.
it's amazing that
It's
the
amazing.
process works. There's sometimes a little bit magic. Do you capture a lot of contaminations if you take these samples out to ambient conditions? From my opinion, these samples are quite robust, and maybe you get some surface contaminations in air, but if you put it into a vacuum, like let's say water vapor, it will go away. So in most cases, we get these clear pictures. What you see here on the top and the bottom, these structures, these are residues from polymer, which comes from this Scotch tape transfer. So this is really the dirty process, but you see like blue sky in the clouds, and the blue sky is here the freestanding graphene, and then you go with the TEM to just analyze the blue sky of your sample.
Okay. Thank you, Professor Absas. It's a wonderful work, and thank you very much for sharing with us these wonderful works.
Yeah, it was a pleasure for me to
Yeah.
give the talk.
Thank you, Professor Absas, and we are really thankful to be our honorary professor. So we look forward for the such kind of the talk with our student during the academic session also, and the collaborations, future collaborations. So thank you very much for your time and accepting our invitation. Thank you.
Yeah, thank you.
Thank you. So now we should move to the next speaker. Next speaker is B. Sundarval from IGCAR Kalapakkam. Yeah. So I request Abhishek to introduce Dr. Sundarval.
Thank you, sir, and thank you, Professor Hans, for a wonderful talk. So, moving on with the event, now let me call upon our next speaker for the day, Dr. B. Sundarwal from IGCAR Indira Gandhi Center for Atomic Research, Kalpakkam, Chennai, India. Dr. Sundarwal joined IGCAR Kalpakkam in November 2001 after completing his PhD from Institute of Physics, Bhubaneswar, and postdoc work at Chinese University of Hong Kong. He visited Tamkang University, Taipei, Taiwan in 2008 as a postdoc fellow and HZDR Helmholtz Zentrum Dresden-Rossendorf, Dresden, Germany as a guest scientist. His area of interest includes ion beam analysis, ion beam modification of materials, and epitaxial growth. He has published over 135 papers in various peer-reviewed international journals and conferences. He'll be talking about ion beam modification of nanomaterials. I would humbly request you, sir, to kindly conclude your talk in 45 minutes, which will be followed up by a 10 minutes Q&A session. We welcome you, sir, and the stage is yours.
Thanks, Professor Abhishek, for giving me a nice introduction. And I also thank the organizers for giving me a chance to give a presentation before this August conference. And now I shall start the PPT. Can you see the PPT?
No, sir. There's a green color button, share screen. You can click on that. Can you see that?
Not yet. Just a minute.
Sir, at the bottom, you can see the seventh icon. It's green color, share screen. Before that, sir, you can open your PPT.
First, you open PPT and then share the screen.
And then go for the share screen option, sir. It's on the bottom.
Abhirami.
Just adjacent to stop video and mute video. After that, 1, 2, 3 numbers.
Sharing everything. Video and sharing one.
There is a green color button, share screen.
Yes. Here, press share.
Now it's yes, sir.
It is coming. Yeah. Now just go to the It's fine, sir.
Okay. Good afternoon to everyone. I'll be talking on ion beams and nanomaterials, and this is the outline of my talk. I'll be and the beam.
May I request you, sir? Your voice is not coming clearly. I think some network issue, sir.
Ma'am, maybe the Professor Sundarwal can turn off his video and then maybe he can give. Then maybe.
Yes, but right now he has. I think he has some network issue.
So you're muted.
Sir, you can unmute yourself. Unmute.
On the left bottom corner, sir.
Left bottom corner. IT support, can you unmute?
I am doing, sir. Wait. Sir, in the bottom there is a button of mute. Please unmute yourself. Left hand side, sir.
They can ask him to unmute. There is
IT support.
They ask to unmute. I'm clicking, but he's not pressing it.
He needs to accept it actually. Sir needs to
Yes, accept. Sir, I'm doing that, but he has to accept that.
Sir, Sundarwal sir, you at the bottom left hand side, there is a button mute. You unmute first. Laliji, IT support. Laliji.
सर मैं मैसेज करती हूँ.
Here, unmute.
Yes.
Now it's fine.
Now it's fine.
Now share your screen, please.
Okay. Okay. Thank you. Yes. There are different type of accelerators, and in electrostatic accelerators, if you see,
Professor Sundarwal, please unmute.
Can you hear me?
Please share your screen.
When I yes, Abhi, இங்க வாமா என்னமா இது வியூ பண்ணாவே அன்மியூட் எங்க இருக்கு
share screen.
Just share the screen.
Share. Share.
Green color.
Share.
Yes. Now it's visible.
Yes, sir. It's visible now.
Say when I make that slide larger size, it is going off. Maybe.
Sir, click on enable editing.
No. If I press, if I press this.
Click on enable editing.
Sir, before going
Okay.
At
Oh,
the top,
yes,
at the
yes.
top you
Enable
can
edit.
see, yeah, enable
Yes.
editing. You click on it.
Yes. I given enable editing. Yes.
Then go for full screen mode.
You can press F5, sir. Just press F5. Yes.
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 Yes. Now it is coming.
Change the slide. Let's see it's working or not. Go
Yeah.
to next
Now
slide.
I'm in.
Just use up and down cursor.
Is it working?
Yeah.
Yes. Now it's
Is it okay? Say Kalpakam, we have 3 different accelerators. One, the tandem accelerator with a terminal voltage of 1.7 million volt. It has 3 different beam lines, and one of the beam lines is coupled with one more accelerator, that is 400 kV accelerator, and these 2 beam lines meet at one UHV chamber where high temperature implantation can be done. This one mostly do radiation damage in reactor materials. This is the first dual ion in India, and other than this minus 10 degree beamline of the standard accelerator, there are 2 more beamlines. This plus 10 degree, this is general purpose beamline. Here we do our ion implantation experiments, and also ion beam like Rutherford back scattering, channeling, pixel, etc. And this beamline is extended further to couple it with inside to SEM that I will show, that setup I will show next. And then this plus 30 degree beam in the left side, this is coupled to a high resolution RBS where you can have a depth resolution of 2 to 3 angstroms, and then we are having a 150 kV gaseous ion accelerator, and here we can do ion implantation. It's connected to another ionolumination setup, and we can do inside to ionoluminations. And these are the facilities. The left side top, you can see that this TEM, which is coupled to the beamline from the right side, and then right side top, it is a HRBS setup, whatever we have here. And the bottom left, it is ionolumination setup. Top corner, one can see that ionolumination spectrometer, and other than IGCAR, in Kalpakam, there is one UGCD facility, and in that one, we installed a 200 kV accelerator with a hollow cathode ion source, where we can do gaseous ions as well as implantation of some metallic ions. And we have one more facility at VCC Calcutta for 30 MeV proton. Here you can see in the bottom left of the slide, you can see this cyclotron, which has 3 discs, and in this there are 2 material science beamlines, and in one of the beamlines we are setting up basic at a high temperature we irradiate materials mechanical properties like creep, and science we do material research, and if you see, we can divide it into some sort of 3 branches. One is mainly ion implantation analysis, and another one is radiation damage. If we take ion, you'll be knowing that it many applications. We can do doping of semiconductors like N-type or P-type, then synthesis of embedded, and synthesize either nanoclusters, or if you put high fluence, we can have buried layer, and whatever compounds are formed, one can even get non-equilibrium states. Visible materials can be made to mix with ion beam mixing and modify the surfaces, and I'll be concentrating more on this surface modification topic. And due to surface modification, there can be hardness or corrosion resistance, and ion beam enhanced diffusion, segregation, crystallization, and there are other processes like sputtering, gettering, smart cat. One can form nanocapillaries, single ion impacts, and different applications are there. And now, when you look at this ions, you know that depending on ion energy, it can penetrate to different ranges, higher the energy range, and throughout the way, it will be depositing the energy into that energy, whatever is deposited, can be either the form of electronic energy loss, that is excitation of target electrons, or nuclear energy loss, like hard state collisions. And for example, if we take 100 kV organ implantation in silicon, helium is having less energy loss, energy slowly, and it penetrates deeper compared to the argon. And so where the ions are stopping, that average position, that is a projected range, these ions will be distributed over some specific width that is due to the straggling. And now nanomaterials, we can synthesize this nanomaterials with this ion, and these nanomaterials, it can be 0D material where you can have spheres or clusters, or 1D nanofibers like nanowire sort of things, and 2D materials like in the previous talk, whatever you had about this graphene. And in graphene also, single line impacts, and we tried to open band gap in graphene. That one I will discuss. And then 3D materials. And once this sort of nanoclusters are, you can either size to nanocluster size, or from bulk you can come down to nano size. So that is top down or bottom up. And this ion implantation can be used to do both these processes. We can go either from bottom to bulk to nanoclusters, that I will show you. And if you look at this nano important, all those interesting properties are coming due to that small size of this nanoparticles. If the size is of the order of this electron Bohr radius, there can be quantum confinement, and because of that, there can be at energy levels or opening of band gaps and all. And if you look at semiconductor, if it is 2D material, here you can see this step size sort of density of states. If it is 1D material, like this one, you can see the shapes like this for density of states. And if it is a nano dot sort of thing, then it will be some Dirac delta function. And if it is a metallic material, when you go to this nano size, you'll be seeing splitting of these energy levels, and splitting will be more in the case of smaller nanoclusters. And when you are doing this implantation, this say I'm telling from bottom to nanocluster size, you are implanting ions one by one. So many atoms are getting embedded. Those atoms clustered together, they form some precipitates, and they coalesce to form the nanoclusters. And the size of the nanoclusters will increase with either increase in dose or increase in the temperature or time of annealing. And for nanocluster from top-down procedure, you can take the substrate, and by the side of the substrate, you keep some catcher foil. Now irradiate the substrate, and irradiate the substrate be sputtered out. That sputtered atoms, they'll be foils. Those whatever are getting captured, that will and one can get nanoclusters out of it. And in case if you want an other, then you keep, for example, here green color is smaller size. Suppose if you want some alloy with lesser concentration of a green element, then that green color element you keep at the center, and at the periphery in large other foil. Here and the silver is larger AG foil. Then in the catcher foil, you can catch copper gold, copper silver alloy nanomaterials, and here in the right side, whatever I'm showing is copper AG nanoclusters, whatever has been prepared. In that one, Rutherford Rutherford backscattering spectra is taken. So here, and also when you are doing sputtering of say some thin film of gold is there, and argon. Once you go on your film gets sputtered out, and on the substrate, whatever is there in the right side SEM image, you can see many nano-size particles, and these particles they have come from a thin film of gold, which is continuous layer, and from that one, with ion implantation, we are sputtering out and we are getting this sort of nanoclusters. So you can get nanoclusters either from top to down procedure or bottom to up procedure. And in this slide, I'm showing 1 MeV silicon ion implanted silica. It is forming some nanoclusters, and these silicon nanoclusters they show say photoluminescence. Can see clusters of a diamond in quartz formed by carbon implantation, and gold nanoclusters in quartz formed by ion implantation, and also depending upon the size of the nanoclusters, your absorption edge or PL will be varying. And we have also got silver nanoclusters in glass, and they show enhanced photoluminescence properties. And there is another thing called core cell nanoclusters. Putting single, if you are doing implantation with single ion, then you will get nanoclusters of only single element. Suppose if you are putting two elements together and anneal, then for example, element A and B, if you are putting, you can get either nanoclusters of A separately and B separately. Okay, both will be there, but they are separate. Or you can form AB alloy clusters, or this A can be at the center and other one may be around it may form a core. So depending upon the bond energy, for example, if bond energy of AB is much less than AA, then this first picture, separate nanoclusters will be there. Suppose if bond energy between A and B is much larger compared to AA bonding or BB bonding, then you'll get alloy clusters. If the bond energy of AA is much larger than bond energy of AB, then you can get this sort of core cell structures. We have done implantation with silver and iron, and in this one we see silver is at the core and iron is at the periphery. And if you look at this photoluminescence compared to silver implantation alone, for silver plus AG implantation, we see the right side picture. You can see that field emission is much enhanced. And by implanting indium and nitrogen together, you can get indium nitride nanoclusters. And say, for example, in zirconium oxide, if you are implanting with argon, you can form argon gas bubbles within this substrate. And then there is something called borrowing of nanoparticles. Here, what we have done, we have deposited say silver nanoclusters on silicon, and on that implantation, we see that we are increasing the surface mobility of the silicon surface, and these silicon atoms, they cover the nanoclusters, and the nanoclusters get buried. It is something like a hammering. This TM picture, you can see that in left side top, one can see many silver nanoparticles on silicon, and upon irradiation, you can see that these particles are penetrating to that. If you see the right side bottom TM graph, you can see the nanoparticles have already got buried into the silicon substrate. So you can modify the silicon. Here we have modified this hammered the silicon nanoparticles into the silver nanoparticles into the silicon substrate. And for example, if you are having a thin film of gold and silicon, bulk film, when you are iterating with the ions, they behave differently compared to, for example, when you are putting this silver on silicon, then we are having a lot of silver, lot of gold particles on that surface of this material. And when we do irradiation with 1.5 MeV gold ions, we see that you see this right side TM image, this gold is penetrating to much deeper depth. Same thing, you are doing it for a continuous stream, it will penetrate only a smaller distance. Graph, whatever you see, in 2 nanometer, it is possible to, gold can penetrate only up to something like 4 nanometer or something. But here, we are seeing that it is going up to something like 100 nanometer with this beam irradiation. And suppose if you are implanting silver into silicon, one can get silver nanoparticles. And if you implant indium and silver together, then one can modify this silver crystal size. And also, when you are implanting silver alone at high temperature, silver clusters are formed at 2 different depths. One is at the ion range, other is off the range. At off the ion range, there will be more vacancies, and at that location, these clusters are formed, giving rise to nanoclusters 2 different depths. When you are implanting with indium and silver together, clusters are formed only at a single depth. This is implantation at high temperature. And now I will come to some implantation with carbon materials. Carbon, if you see, there are different types of carbons like fullerene, carbon anion, nanofiber, nanotubes, diamond-like carbon, amorphous carbon, nanoscale diamond. We will be talking about nanoscale diamond, diamond ash, diamond nanoash, like that. I will show you some this diamond material, and depending upon the size of the grains, it can be micro diamond, micron size, or nano diamond if it is less than 100 nanometer. If it is less than 10 nanometer, it is called a ultra nanocrystalline diamond. And whatever ultra nanocrystalline diamond I talk about, grain size is 3 to 10 nanometer. And this material, that advantage is that 3 to nanometer, whatever it is, 3 to 5 nanometer, it is diamond. But at the boundary, it is having graphene, some graphitic material is there. So it has some exotic properties that I will show you. And once you are having this ultra thin, ultra nanocrystalline diamond film, one can get a smooth surface compared to this microcrystalline diamond. And suppose if you take this for flat panel display and all, people use say an array of molybdenum tips. On that molybdenum tips, if you coat material, you can get electron emission at lower voltage. Normally in TV, suppose if some 1000 volts is required for emission, with the covering of this sort of material, one can get electron field emission at something like 10 or 30 volts itself. And this material, it is having very low friction, and one can form this sort of nanofiber tube, or you can coat it on AFM tip to have a very large lifetime. And also this material, you can use it for functionalization and use it as a biosensor or retinal implants. It has many applications. And also, if one does, for example, culture growth of certain material, a certain biomaterial, here this culture growth will be faster compared to simple glass dish. And we have done this electron field emission with ion implanted samples. And for electron field emission, what we have is a molybdenum, and there we apply something like 1000 volts, and below that there is the sample, and gap between the sample and the tip is around 5 micron. So by varying the voltage, we can measure the tunneling current. And if this tunneling happens at a lower voltage, then our electron field emission properties are good. And we have done gold implantation in this UNCD film. And if you see the bottom left grain curve, if you see at lower tannon itself, we get that electron field emission. So this lower curve is coming due to the implantation of this gold into the UNCD. And this enhancement in field emission, it is due to the formation of gold and nanoparticles into UNCD. And also there is a formation of nanographite. So this gives enhanced conductivity and also enhanced electron field emission properties. And this UNC material, we have coated it on nanowire, and then we have made some. You see that, for example, if suppose if there is a UNCD on silicon alone, if the film is on silicon alone, then that emission takes place at 230 volts. But if you are doping it, say emission is taking there, it is taking around 3 volts in UNCD and silicon. But if you are putting it on this UNCD on silicon nanowire, then we can get that much lower voltage itself. We can get that this emissions. And also this ion implantation, it graphitizes this material, and this Raman shows that there is for example, this Raman around this 1550 centimeter inverse, that corresponds to graphitic peak, and that this material is getting graphitized upon this implantation. And in also, if you do this irradiation, we can break up this MCD grains into nano size grains. And this ion implanted UNCD samples, we have studied mechanical properties, and we see that this friction coefficient is decreasing upon irradiation due to the formation of due to the graphitization of this material. And then we have also done some irradiation experiments on graphene oxide. And when we do irradiation with different ions, nitrogen, argon, silicon, or gold, with different ions, when we do the irradiation, this oxygen is sputtered out, and we see that this material is converting to graphene when you are implanting the 5 MeV gold ions. And this in the right top second, if you see, you can see that honeycomb structure of graphene obtained with ion implantation with ion implantation into graphene oxide. And by implanting cobalt to silicon, one can form a buried cobalt disilicide layer. And that for getting buried of a few, one has to do high fluence. But when you are doing only at low fluence, something like 5 into 10 power 9 ions per centimeter square, or up to 10 power 12 ions per centimeter square. Each ion impact related to the impact. For example, if you are implanting in semiconductors, you will get crater-like features. If you are implanting with implanting into insulators, you will get sharp tips-like features. And we have implanted this gallium. Some craters are there, and upon higher fluences, these craters overlap and surface gets modified. And in gallium, whatever defects are formed, those defects can annul out with time. Here I shown some reference from Argon National Lab, where with inside to TEM, they have shown that those craters, how they are getting formed, and also they are getting annealed out with time. And I told that we have done some ion irradiation in graphene, and graphene sample keV argon monomer, and in some samples with 70 keV argon dimer. And here we see that there are this rightmost image in the top. You can see that some craters are formed. Okay, and in between, and in the left side, and these craters, they properties. You know that graphene is semi-insulating, and in these samples we have done this scanning tunneling spectroscopy measurements. That is IV curve, that is local IV curve we are taking with STM tip. This left side bottom, we are seeing this IV curve taken at ion impact, and also at positions away from the ion impact. Okay, and what is the main result is that where we have put the beam, at that place, graphene, semi-metallic graphene is converting to metallic nature, while in between the ion impacts, we see that there is a band gap opening. That band gap opening here I marked in the bottom right picture. It is some 0.25 eV. Okay, here in the bottom right picture, where this di by dv versus v is shown, two graphs are there. That blue one, that blue color one, which is at the bottom, there you can see in the band gap there is a 0.25 eV opening. This is in the planar region between the ion impacts. At the ion impact, you can see that this density of states is much higher, and it is showing, and and etch it, you can this set of capillary, and some specific angle ripple-like pattern, and after getting this ripple-like pattern, you rotate the sample and do the irradiation again. Then you'll be able to get this set of nano patterns. So by changing the ion energy as well as this angle, you can modify these surfaces. And with ion, you can do ion beam mixing. For example, this silver and iron are immiscible material, and this right side image, you see it is a SIMS image. That bottom one, you see two peaks. Those two peaks correspond to ion signal. Okay, in between these two is silver, and upon irradiation at low temperature, something like 110 Kelvin, we see that iron is mixing throughout silver, and you see continuous layer. When we do irradiation at low temperature, mixing is not that good. And this is ion enhanced diffusion and segregation. This here we implanted iron 40 kV iron into substrate. Whatever smaller peaks you see, those peaks are, once we go for higher fluences, then there is ion beam enhanced diffusion, and it is penetrating much deeper. Say ion range is only something like 30 nanometer or something, but with higher fluence, it is diffusing up to something like 250 nanometer, and it is forming FEG. And if we irradiate still further, then this can desegregate to give separately. They can then I told about RP/2 effect. Say when you're doing irradiation at half the depth, there will be more vacancies, and there, in addition to cluster formation at ion range, at RP/2 also there can be formation of nanoclusters. And we have done this ion irradiation at low fluence in some ferroelectric materials, and left side whatever you see, top one, that is surface morphology, and right side, that is surface morphology upon irradiation, and then that middle picture, this is a piezoelectric EFM image, and here you can see a lot of electrostatic domains. Upon irradiation, these domain sizes are becoming smaller in size, because whatever ions we are putting, some ion traps are formed into that insulating material, and this asymmetry in this formation of these domains, we get smaller size domains in this set of nanoclusters. And by irradiating ions into certain materials, we can modify these say some electrostriction properties can be modified. Electrostriction means, for example, you imagine a string, and at the bottom of it you are having a load. Now between the ends of the string you apply some voltage. Once you apply some voltage, the string can contract and lift up the load. Okay, that is the electrostriction. And in the ferroelectric curve, if the curve area, if it is smaller, then electrostriction coefficient is properties. And in this material, upon irradiation, we have enhanced this electrostriction properties. And by implantation of iron in germanium, we got negative magnetic resistance in these materials. And by implanting gold, by implanting either cobalt or manganese in gallium nitride, we can form ferromagnetic semiconductors. For spintronics, connecting where spins can control, either by applying magnetic field, you either make it spin up or spin down. And for that, one has to make room temperature ferromagnetic materials. And in this one, you could get room temperature ferromagnetism in the case of M1 implanted gallium nitride. And in gallium arsenide, when we implant manganese alone, this magnetism Curie pressure, antimony together the nanocluster formation, and we can get ferromagnetism at room temperature also. And we use ion beams for making simulating the radiation damage produced by neutrons in nuclear reactors. And normally this nuclear fuels, if you see in breeder reactor, once you put the fuel rod, in principle, even for 40 years, you should be able to keep the fuel because it is breeding. But once in 2 years, it has to be replaced, because during fission, a lot of neutrons are emitted, and these neutrons, they make damage on that clad material which holds the fuel. And it makes the material swell. Once the material dimension is increasing, the fuel rod being straight, it will bend like a bow. And so only they allow some 10% expansion or something, then they remove it. But now one group is working with different alloys which can withstand higher irradiation influences. So that modified steels we start with swelling in the reactor. That for studying swelling in the reactors, if we take one has to keep the material for more than 2 years time. But if same thing is given to us using ion beams, we can implant this 5 MeV nickel ions and co-dope it with helium using dual line irradiation. And with the 2 beams putting in, we can simulate reactor-like environment at high temperature, and we can see that that swelling, how much the material is swelling, that we can tell within some 5 to 6 hours instead of waiting for, because our heavy irradiation, it makes 5 orders much higher density of defects. Because of that, rate will be fast when you are using these ion beams, and also this one is not radioactive. So for screening the materials, for example, if 10 materials are given to us, we can do this experiment and tell which material swells least. So other mechanical properties people can study in that material. So this ion beams have a lot of applications in material science, specifically nanomaterials. Some of the results I have shown, and you are welcome to visit IGCAR Kalpakam. Thank you.
Thank you, Dr. Sundarwal. It was a nice presentation, and within this short period of time, you have covered so many examples, so many applications of ion beams, ranging from low energy from keV to MeV range. And also you have shown the different facilities available in your center. And I somehow missed, you had talked about some proton accelerator at VCC Kolkata.
Yes.
So
it is 200 kV accelerator. It and it has a hollow cathode ion source, so we can put say this bottom right.
Okay.
So we can do gaseous ions implantations. Is 20 kV, and some elements like gold or few metallic elements.
Okay. So at first, let's see whether there is any queries from the panelist. Is there any question?
May I ask one?
Abhishek, you go ahead after that.
You, ma'am, please. Please, you.
Achha, okay. Sir, I have a small query regarding the fast neutron damage, which you talked about in your second last slide.
Yes.
So I just wanted to ask, when you're simulating it with 5 MeV nickel ions, does the rate at which neutrons go and these 5 MeV nickel ions will that affect the swelling? I mean, the damage which is created by the neutron, will it be same as that created by 5 MeV nickel ions in a very small span of time? Or will that be, there will be some...
The processes are different.
Okay.
There is no one-to-one correspondence.
Okay.
And what, for example, say, for example, radiation, suppose if there is some 8% expansion, swelling is 8%, say. When we put same amount of defects, that neutron, how many defects it is putting, dPA, we tell in terms of dPA, displacements per atom. We put same dPA, but this whatever defect at a lower rate, and as well as because of that there is no correspondence. But we can screen the material. Suppose I told that some 10 different materials are there. If those 10 reactor, test reactor for 2 years. And after 2 years, you get intimation. You sort of this material swells the highest. This one swells the least. With neutron, you have some. When we do with ion, it in there you have to wait 2 years. Here in 10 days or 15 days, we complete the irradiation and give the same order. Even though there is no one-to-one between neutron damage and heavy ion damage, we can use it. You can use it for ion beam simulation for screening the material. We can tell this material swells least like that.
Thank you so much, sir.
Sir, yes, sir. So I had two questions. First one was that when we were implanting on the semiconductor surface and the insulator surface, you told that on insulator it was peak shape, on semiconductor it was circular kind of shape. So what was the reason? Yeah, correct. So what was the reason? Like, why is there a difference in the structure which is forming?
Basically, during this latest, whatever is happening is rearrangements of these atoms. Either they cause, say, for example, if there will be formation of whatever interatoms are there. There will be formation of interatomic planes, and also there will be formation of vacancy planes. And these interatomic planes, they'll be collapsing into that vacancy planes, and they form some sort of case of semiconductor. While in the case of insulators, there they enhance the density of the material. That ion track, whatever is going through, those things they increase the density of the material, making it pop up.
Okay. And so I wanted to know that we are synthesizing nanomaterials through this ion implantation approach also. So did you compare the two different approaches like chemical synthesis and ion implantation synthesize nanoparticle, and did you study what's the difference in properties we are getting? Like, is it better in any way?
So this graphene, the graphene oxide, whatever I showed, that is with chemical method only, Hammer's method or something.
Yeah,
and in that one, by irradiated graphene in that one. But that particle property, I think, depends upon the size.
Okay, only
Size
on
of the
size.
material.
Yeah. Okay.
This implantation, that will be the same.
Okay.
So, Dr. Ghosh, if you have any question, or if you would like to make some comments.
No, I don't have any question. It's a very nice talk, Dr. Sundarwal.
Yeah.
Yes, after 2 years, I remember.
It's nice
I
to
see
see
Anagi
you.
last time. Yeah,
Yes.
shown all the facilities. It was really nice, very fascinating. Thank you.
Okay.
Thank you.
So, Sundarwal, I have a few questions.
Tell me, sir.
You have, yeah. So I am your junior, probably. I am
Tell
Somunath
me.
Bhupen. Yeah. So you have talked about iron silver multilayers was irradiated by some energetic ions, and you have mentioned that there is a mixing,
Mixing.
and then there is segregation.
That is mixing and segregation in the case of iron and germanium.
Okay, it's not for same ion.
Only once we go for higher fluence in germanium, it got segregated. Initially, it was forming compound formation, and later
yeah.
Here it is. This is silver ion. This and in this one only mixing. Here in this one, we implant iron in germanium. When we implant iron in germanium, initially there is a FeGe formation. If you see this XPS core, this top core, this FE-GE phase, this right side one is dominant compared to FE. But once we go for higher fluence, this peak corresponding to ion to peak, that is getting enhanced.
So this is due to the radiation induced radiation enhanced diffusion at higher fluence, that initially due to ballistic mixing there is a mixing between two materials, and when you go for higher fluence then they demix.
Defects also propagate into the material, and defects are also involved in this enhanced diffusion mechanisms.
Okay. And another one, so if you are talking about the hammering process by the energetic ion beams, that you can put the nanoparticles on your sample, then using energetic ion beams you can bury it into your sample.
Yes.
So could you please go to that slide? So I want to see that at a particular depth they are buried.
It will be at much lower depth only. Where it is. Yes. It is within 10 nanometer.
So then if you increase the energy of the incident ion, so can you control the depth?
It should be possible.
Sorry, it's possible.
It should be
Yeah,
possible.
yeah. That's my question. So it's a very nice technique that one can control the depth at which they want to bury the nanomaterials in their sample.
Yes.
Yeah.
This is done by Satyam's student.
Okay, thank you very much. So for your nice presentation, and you have covered many examples. Thank you again. So move to the next speaker.
IT help desk, please make rights to Tanuja Mohanty ma'am. Lalitji, please make her co-host. Abhishek, you start.
Okay, ma'am.
You introduce that.
Yes, sir.
Yeah.
Surely, sir. Thank you, Dr. Sundarwal, for your great presentation. Moving on with the event, let me now call upon our next speaker for the day, Dr. Tanuja Mohanty from JNU New Delhi. Dr. Mohanty is currently working as Assistant Professor in School of Physical Sciences at Jawaharlal Nehru University, New Delhi. She received her PhD degree in physics from Utkal University, Odisha. She has won many awards and honors such as DST Dart Fellowship, DST Fast Track Young Scientist. Her research interest is really vast, such as experimental condensed metaphysics, nanoscale semiconductor and metals, graphene and graphene-based nanocomposites, ion interaction with solids, and many more. Today, she'll be talking about controlled surface electronic modification of 2D materials by irradiation engineering. I would humbly request you, ma'am, to kindly conclude your talk in 45 minutes, which will be followed up by 10 minutes Q&A session. We welcome you, ma'am, and the stage is yours.
Thank you. At the outset, I'm thankful to the organizer, particularly Dr. Richa Krishna and Professor Sinha, for inviting me to give a lecture or talk in this conference. So let me share the screen first. Just 1 minute. I think it is.
Yes, ma'am, it's coming.
It's coming, right? Okay. So let me do it to the play from the start. Okay. So myself, as it is, I am from School of Physical Sciences, JNU, and I have done a lot of work. I mean, even during my PhD also, I have worked in IUC, nuclear science, etc., on superconductivity. Then after, I have worked in nanomaterials, particularly in oxide nanomaterials, semiconducting nanomaterials. Then after joining JNU and once in 2006 and once is after the discovery or the Nobel Prize, it was received on 2D materials, particularly on graphene. I have started work on that, means particularly my student had given the synopsis on that. So I had worked on this, the word controlled surface electronic modification materials by irradiation engineering. The word irradiation engineering is the conference is on based on that, so the different one. Then surface electronic modification in the morning means surface electronics means it will be mostly the surface potential study, which already Professor B.R. Mehta had told, and I will tell about that, because we had worked on a lot since last more than 12 years on the surface electronic studies of different materials. So at the outset, let me thank IUSC, because for this presentation, the work which was done was mostly the accelerator-based work. So the IUSC, definitely the accelerator or the ion implanter that has been used. So that is and Dr. Kanjilal for his suggestions at different times. And some of my PhD students who have already completed and ongoing, their work I'll present, because it is not possible to all the work to be presented which are done using this ion beam. So they are Dr. Mukesh Mishra, Dr. Jyotish Sakyadu are doing postdoc, and Mr. Sanjeev Kumar and Mr. Tanmay Mahanto. Their work I'll present all these works, and they are attending the conference. So although it has been the theme of the conference, the today's talk is mostly on 2D materials. So even then it has been told, but nevertheless it has to be, I can repeat it so that I think repetition will not create much a problem, because I find the most of the audience are the students in comparison to the teachers. So we see the 2D materials that starts with the discovery with graphene, and particularly it's a great excitement after 2010 when the scientists both Gaim and Solovo, they got the Nobel Prize, and they found that it is the graphene had a lot of application. The moment graphene is found to be more application, so the research goes on each day that any element, even in superconductor, in anything, like whether we can also make it like a thin 2D material, and the 2D material, because you know the two-dimensional material before that in the nanostructures, that it says about the quantum confinement effect itself. And particularly in 1983, when there was a discovery of like quantum Hall effect, the quantum Hall effect was discovered in graphene, and it was in 1983, it was at the interface gallium arsenide, gallium LGS. So it was seen that if we have a thin layer, if we have so much charge carriers, whether it is possible. So graphene is the first 2D material, and it has this hexagonal structure. And in the morning of talk also you have seen that it has the Dirac fermion, and it has the E versus K relation. The dispersion relation is linear. So now I can go to the next when it is the molybdenum disulfide. That molybdenum disulfide, when I say that it is a transition metal dichalcogenides, because in my talk I will just cover all these materials to some extent, even then their nanocomposites I will not cover. So the transition metal dichalcogenides, why we say that them? Because the transition metal in this region where M stands for this, titanium, zirconium, HF, NB, molybdenum, WTC, and these transition metal along with this side and the chalcogens, not oxide. Abhindan oxide is a chalcogen, but particularly sulfur selenide tellurium. if we combine them, then we are getting a transition metal dichalcogenides. One of them is the MX2, which is MOS2, that can be of W, means tungsten sulfide also. And among them, some of them, because of their periodic table combination, they behave in a similar way. So in that case, even it is a MOS2, then it is like the 3 layers SMS, the 3 combination that we say as a single layer, although they are in 3 level. And then we see that these are also like in a van der Waals bond. The vertical one, like the layers, they are connected with van der Waals bonds, and it is easier to remove them, because it is seen that from graphite, because a layer is removed by the Scotch tape, or a layer is removed by the sonication and centrifugation. So a layer you remove by any way, that makes you, if you can achieve in an atomic layer, then it will say that it is a 2-dimensional material. So the lacuna in the graphene was that it was although it is a very high charge carrier density, mechanical strength, everything which you have seen or have heard, but there is a lacuna is that it is the band gap is 0. So sometimes for some applications you need the band gap. So sometimes you dope with the graphene with some material to open up the band gap, or you just do it or the search goes on further to find out some material which is like these materials. They are indirect band gap when they are in the bulk state, but when quantum confined, it goes to a direct band gap and the band gap increases, and that can be helpful for the application in the optoelectronic devices. Okay. Why it is not going? Okay. So just 1 minute. So the next is like hexagonal boron nitride. Hexagonal boron nitride, of course, the lecture was not much on that, on hexagonal boron, some partially it was there, straight up. So hexagonal boron nitride, it is on the other way around. It is on the other way around means graphene doesn't have any band gap. The hexagonal boron nitride has the band gap of 5.9 eV, or you say it is 6 eV. But in all these cases, they have the bonds. In the graphene case, it is a hexagonal bond having the only carbon in the hexagonal ring. Here there is a B and N atoms are there, and also there are layers. And if you are some 4-5 layers, then you don't say they are that bulk hexagonal boron nitride. Rather we say at the BNNS, that is boron nitride nano 6. We normally say the BNNS. In my presentation, I will just our recent work, which is this year work, that will say it on BNNS. So that we say it is on the BNNS means it is like it is not exactly a single layer, but it is there are many layers which are present in the 4 to 5 layers, and you have the layers like you have hexagonal boron nitride, and that can be similar as nano ribbon of carbon. So it is an allotrope of graphene, which we say as white graphene, and it is a fullerene because it is transparent in nature. So there is the nanotube, and similar to fullerene, it can be done. So B and N atoms are strongly bonded into the honeycomb lattice. So before going into the, so now we see that these are the some of the 2D materials which are mostly studied currently, but there are many 2D materials which are studied and for use for applications. Towards the aim, with the focusing on the work which I am going to present is that the irradiation engineering, and normally you know that irradiation, if it is in implantation, then it causes the alignment. But in particularly in irradiation, if you use, then we use the irradiation and irradiation to introduce some of the defects. And these defects, when it is introduced, we use another word which is a defect engineering. So defect engineering means having the defect at particular places, means defect doesn't mean that defect is a bad for the system. Defect means it can be very helpful for the system also if it can be engineered in a particular, it can be arranged particularly. And defect, it can be like a dopant can be a defect, any additional thing can be defect. Suppose graphene is there, I will go on, then graphene oxide, then for that graphene oxide will be a defect for the graphene. So in that case, what kind of, then before going into that irradiation induces the defects, so let us see that what kind of defects can be in these 2D materials. So this 2D materials have some structural defects, and that can be like not in a symmetric form, which should be ideal case, but it can be like a vacancies or odd atoms, or it can be a substitutional doping. So substitutional means in place of a particular, suppose N, there will be B. In case of MOS2, it can M, there will be S. So this type of defects can occur, and this can be introduced in either in the during the synthesis or the subsequent treatment. And here it is like you say, it can be in 2-dimensional defect, it can be in 3-dimensional defect. So when it is a 2-dimensional defect or a 3D defect, that goes mostly happen in case of heterostructures, which I am not going to present now. So I have just taken this part of it from Lane et al, that what are the defects can be produced in 0-dimensional and 1-dimensional material. So 1-dimensional can be edges, it can be wrinkles, so it can be edges and in a one side defect. So here it is like edges, the grain boundaries here completely the defect and the lateral heterostructures. So the defects in graphene, so what are the defects in graphene can be there? That one is the Stonewall's defect. So the Stonewall's defect that results from the, if a single pair of carbon atom that gets rotated. So if it is rotated, then you will have a pentagon and heptagon instead of a hexagon. So the number of carbon atoms remain same, but that is not the ideal hexagonal shape. So then there is the Stonewall's defect, and that is mostly like intrinsic type. And the single vacancy, you have a single vacancy defect, and also you can have a di-vacancy defect combined together, tri-vacancy. So you say it as a multiple vacancy defect, and it, so those defects, so this left results, they are like TM structures. The other, this side design is from the DFT calculation. So now in hexagonal boron nitride, what type of just 1 minute, in vacancies in MOS2, what type of, like we see in graphene. So similarly in MOS2, what we can see, so MOS2 you can have like it can have the VS means only sulfur vacancy, it can be disulfur vacancy, it can be molybdenum sulfur, or it can be MOS6 and MOS2 MO, like this similar type of defects can be produced. And then what kind of defect will be produced, that depends upon the particular energy formation energy. So the defect formation energy is minimum for S vacancy creation from 2 to 3 eV, and for MO vacancy it is 8 to 9 eV. So SHI, that is the swift beam irradiation, is a very and it is nothing like a 2D material we are doing it. It is because the audience is mostly the people who are using the ion beam. So it is known that swift and irradiation with a particular control dose, it can be a tool that can be controlled and targeted to exit to defect generation ion induced defects. So now the similar, if we go to the HVN, so HVN also you find, which is a theoretically predicted, and the similar as Stonewall's defect, that is the rotation of the hexagonal ring, and the boron-boron defect, which is B, that is the boron-boron defect. Then C is the tetrahedron defect, which you can see, and the antisite means antisite here, that where the boron should be there, the boron is not there. I mean, nitrogen should be there instead of nitrogen, the boron is there. So you said it as antisite, and B interstitial vertically, and then HBN. So here is there is a interstitial in between the two layers, which ideally should not be there. So these are the number of defects that can be produced in the in these materials, 2D materials, similar to as the other materials, whether it is oxide or metal, oxide or semiconductors. But here, in addition to that, because it is a layer one, you can have this type of defects also in between the layers also. Now, before if I go means later on I'll come to how the graphene ends, but is it here. So there are different ways of synthesizing. One is one is here graphene and this one. So graphene is normally synthesized if it is by Scotch-Tape method with some mechanical etching. It can be by CVD, which is CVD uses like this technique. Now it can be of the sonication process that you make the layers, and the same sonication, fundamental sonication and centrifugation, that makes the process that you break the van der Waals bond. So that happens also when you do the HBN, or when it is done for the, whether we do it for the HBN, whether we do it for the MOS2, or whether we do it for graphene. But besides that, in graphene, we normally use the Hummer's method. Hummer's method is like a method where it starts with graphite, convert it into graphite oxide, then reduce the graphite oxide, first break the layers, and then it goes to graphene oxide, then you reduce it. So that goes into a Hummer's method. So and in particularly, if we say also in like HBN, there's also the similar process. So HBN is like a bath sonication and centrifugation. So this process goes on one by one sequentially, which goes sonication and centrifugation. Centrifugation, the role of centrifugation is to differentiate between the higher mass and the lower mass, and the sonication is to vibrate it so that to break the van der Waals bond, and the time, the chemical used to break the van der Waals bond. So all these things helps in to create a single 2D layer, a single layer 2D material. And also we can use it by the CVD method. So CVD is that for HBN, you can use the diuren and ammonia. For graphene, you use the carbon base. Then you have this H2 and your methane you have to use. So this also you can do it by sputtering. So, but commonly used is either CVD or the chemical exfoliation method. So now, so what we have seen that these are the ways the defects can be produced, and in this there's the synthesis process. Now there is a word in my talk is that surface putting, it is a surface electronic. The word normally we use for our manuscript and papers, that is we say surface electronic. Why? Because this we use the technique scanning Kelvin probe microscopy, that is the SKPM, or you say SKPFM. So scanning Kelvin probe microscopy, where it may study the surface, and the surface means indirectly that surface says what is the Fermi surface, how the actually surface study. It is not the atomic force microscopy study, rather it is the study of the mapping of the Fermi surface. So Fermi surface, because it is related to the availability, the presence of electron, because the maximum electron present in the surface level, that you say Fermi surface. So if the electron is removed or displaced, then you say that the Fermi surface goes on, off, whatever. So therefore, by measuring the Fermi's, measuring the by scanning Kelvin probe microscopy, indirectly we measure the Fermi surface. So we say that it is a electronic surface electronic study. So in the morning, you have seen Professor Mehta, what he had said about the scanning Kelvin probe technology, and it is between, like, if you have the 5 sample, the 5 sample actually depends upon the EKIS, the like electron affinity, plus EC minus EF. EF is the Fermi surface level and EC is the conducting band energy. So what it happens, in this case, it is not atomic force microscope. It is based on the parallel plate capacitor. And if you apply, means initially the phi of the sample, and you have a tip, which is the tip is normally the gold tip, and it has a fixed work function. Now, when you make it like our system is not related to atomic force microscopy only, it is from the KP technology, which is only focuses on the measuring the contact surface potential. So we say it is a contact surface potential because, like, when you apply it, that is connected, so it measures what happens when the two metallic plate, one metallic plate is your sample, sorry, the other metallic plate is your gold tip. So when they are metallic plate are like your, it may not be metallic, it can be like the semiconducting. So when they are close to each other, the electron flow from the lower work function to the higher work function until the equilibrium Fermi energy is there. So when there is a connection, a voltage is developed. When the voltage is developed, the system will try to make it the potential, if biased potential you have to apply to nullify the current. So that through the calculation also has just shown. So I'm not showing it again. So to make the, how you will know that how much potential difference is there from the between the contact tip and this. So then you make it in such a way that to nullify the current. So that case it makes that how much potential the retarded potential you have to apply, that is the VCPD, so that the current flow will be 0. So then the VCPD, that is the contact potential difference, is the phi tip minus phi sample by E. So that is the phi metallic tip and the sample work function. And this is nothing with ion beam, but let me just tell you that this is like the mapping of the work function of the scanning Kelvin probe. And it is for like when most of the people who start with graphene, they start with initially with the humus method, where they go from the graphite to graphite oxide to graphene oxide, to reduce graphene oxide, to reduce graphene oxide, more reduce, more reduce. So we have marked in our paper, it is reduced graphene oxide 1, reduced graphene oxide 2, reduced graphene oxide 3, likewise. So in that case, it is like we have seen the variation in the scanning this CPD value, that is the contact potential difference. So you measure the WF indirectly from the contact potential difference. So actually directly we measure the contact potential difference, making the I to be 0, the current to be 0, and indirectly we may found out what is the work function. And knowing the work function, as you know, so many devices, they need the work function, the application of work function is there. So this was when we do it, we have seen in 2013 research, like although it is nothing with the ion beam, it was only the RBS was done to study what is the content, oxygen content. So we have seen that the CPD and the oxygen content, they are almost goes in a similar way, and they find the CPD value that goes linear relationship, the linear fitting of CPD variation during decreasing oxygen content because we reduce it to get it from graphite oxide to graphene. So then the work function also that CPD value, oxygen content, CPD value increases with oxygen content, that means WF decreases with oxygen content. So yesterday talk, Dr. Ambus Tripathi, he had also told about the ion beam effect on graphene. So although we have done it on graphene, but I am nothing to tell more on it. There is similar result or something more different where we find the sputtering, but I'll just tell our some previous result. So which was the TiO2 nanocomposites, and it is the nanocomposites are graphene TiO2 nanocomposites exhibited this variation, and we had used the synthesis slowly for G into TiO2 to find the like instead of because the graphene that I am not presenting the graphene whatever we have found out, so we have used the graphene TiO2 because TiO2 also we have seen about the role of the ion beam as well as the work function.